there, my name is Alejandro, and welcome back for day 102 of me doing the Daily LeetCode challenge until I reach 1 year's worth of win contributions here on GitHub. So today's problem is from October 26, 2024, and let's get straight into it. Okay, today we get LeetCode hard, problem 2458, height of binary tree after subtree removal queries, of course. Okay, so quick disclaimer before I read the problem here. My girlfriend and I are going to watch a Forest Black concert that I need to leave here by maximum an hour and 10 minutes from now. So I said that I hope I'll be able to solve whatever LeetCode is given in front of me in an hour's time, and of course we get a LeetCode hard. But nevertheless, I will try to fit this under an hour. It'll be a big goal. I haven't read the problem yet, and let's just get straight into it. Okay, you're given the root of a binary tree with n nodes. Simple enough. Each node is assigned a unique value from 1 to n. You're also given an array queries of size m. Okay, cool. You have to perform m independent queries. Okay, cool. On the tree where in the ith query, you do the following. Remove the subtree rooted at the node with value queries of I from the tree. It is guaranteed that queries of I will not equal to the value of the root. Okay. Return an answer array of size m, where answer of I is the height of the tree after performing the ith query. Oh, so we don't even have to delete nodes. Ah, okay. Ooh, that just gave me a brilliant idea, right? If you're supposed to, delete two subtrees, and like at any node you see the left and the right child, and it's like, oh, those two have like been quote unquote deleted, quote unquote. Then it's like, oh, I know that I can't fetch the height down there. That's actually very cool. And okay, in the worst case, it's an O of mn algorithm. Let's see what. Okay, n is 10 to the 5. Minimum of n and 10 to the 4. See, that's very interesting. Why? Minimum of n and 10 to the 4? I have never seen something like that. What does this mean? It's like n log m or something? Or log n m? It's like, you know how usually you see, like, you look at the constraints to get a hint of the time complexity. Like, this is super sus, right? Like, this is sus as hell. Like, why is it not able to go to the 10 to the 5? If I have two 10 to the 5s, it's like 10 to the 9 and 10 to the 10 are both, like solutions you can't get to. It's like square root of this times 10 to the 5? What the heck? Okay, that's a very, very interesting number. Maybe this, it's like, on average it's log n, so it's like 5 times 10 to the 4. All right, so I got to write a solution that it cannot be queries times root. So I can't really, I have to compute the height once, which, what is this? Is this a binary search tree, a binary tree? Like, binary tree, does it follow? No, so here both the numbers are greater, right? Okay. And can I be given something that is not height balanced at the beginning? Maybe it's like, maybe for each node, I keep track of the heights of the two nodes below, right? Okay, maybe idea is for each node, keep track of heights of both nodes below. Can do so using a hash map / dictionary. Then write a get height function, which first queries if a child has been deleted whose effective height is then 0, to calculate height as either 0 or the height stored inside of the hash map in case child is still alive. Okay, we also got to think about recursively, right? So, like, if I have the height of a child and I kill one of that child's children, then I just messed with the height of the big child. Okay. So I'm gonna recursively mess stuff up. I can't just keep calling the height of the tree, right? Like worst case, the height of the tree. Oh, I guess it's min of n and 10 to the 4. I get. They should have just said it's like less than or equal to n, right? Like why leave 10 to the 5 nodes alive at any point in time, right? And here it's answer of I is the height of the tree after performing the ith query. Jeez, dude. Like the simple way, obviously, which will just not allow complexity wise, is like, for each query, delete the actual nodes. Another thing is that getting the height becomes cheaper and cheaper and cheaper as you delete subtrees, right? That's another thing that's very interesting. Maybe what I do is I traverse the entire binary tree and I keep track of everybody's parents, right? Because it's like, how like in a heap when you percolate or whatever and so on, you need to go up through the parents. It's like if I give every single node, info about, their height, and it's like I delete some subtree, I need to go up inside of the tree and start telling, yo, my daddy, like, listen, dad, like, these children of yours, like, they died, bro. And so now your height is actually way smaller. And he's like, oh my God, my height's way smaller? Then he goes call his daddy, which is actually grandpa. And then grandpa says, like, oh my God, my grandchildren are dead. And so my height is now smaller. And so grandpa goes talk to his daddy, who's now, great grandfather. And he's like, oh my goodness, my great grandkids are dead. And so then my height is slower and slower. And then you just, keep going up and up and up and up until the root of the tree, right? So maybe, okay. Definite, that's an idea. I want to do that, right? So self.daddies or self.parent, yeah, is equal to this. Here we'll do self.populate parents. Node to parent node. None for root. Here we'll do the root, and it'll be none. Right? So here we'll do populate parents with self, root, parent node. All right. If not node, return. Here we'll just call this root and parent, whatever. If not root, then return. Otherwise, self.parent of, first of all, assert that root not in self.parent. Self.parent of root is equal to parent. Here self.populate parents with root.left, and its daddy is going to be the root. Then self.populate parents with root.right, and its daddy is going to be root itself, and then here we just return, right? So here we populate the parents, we populate the daddies, and so now for each node we essentially have a mapping, like here we might as well do val to dot val. Okay, that way it's like print self.parent, and then here return what? We return a number. What do we return? We return an array, i.e. like a tree. None. Where? How? I do if not root then return. So root.val cannot, bro. What? Oh, parent.val. If parent else -1, just for the root node. Yeah. So yeah, so the root node, yeah, in this example, yeah, the root node has no parents, so it's -1. 3's daddy is 1, which is good. 2's daddy is 3, that's good. 4's daddy is 1, that's good. 6's daddy is 4, that's good. 5's daddy is 4. 7's daddy is 5, right? So now we have access to the parents, which is actually very good. You know, one thing that we could do is I really wish I knew how to use AVL trees again. I asked before on the channel, like, you know, I try to figure out if there's a library that I can use for AVL trees. And there was like someone on my channel like commented about like, you know, the sorted list library that I took a deeper look into. I didn't like that some of their time complexities were like, you know, like n to the 3/4 or 5 over like 4/3, and instead of like n log n. I was like, oh, that's kind of weird. And it's like, you know, it's allowed for insertion source. I want to be able to, you know, I should just learn the skill of like implementing AVL trees from scratch. That's just like something in the back of my toolbox for solving LeetCode problems. Because honestly, whenever I deal with a tree, like I might as well convert it into an AVL tree and just make my life super simple to keep login operations, right? But for the sake of this problem, we'll try to do things without using an AVL tree. Okay, self-taught parent. But again, for LeetCode hard, it could be that, you know, they expect you to know something like an AVL tree. So we got to watch out. Now I got to think. So now we have an ability to query parents. Now we have to be very careful when we delete a node, right? When we delete a node, okay, when we delete something, geez, I delete an entire subtree, bro. So let's look at an example. Queries is equal to 4. So just delete the entire subtree of 4. So yeah, the height after that is 2. I see. So like, you know, like for something like this, it's like here, like, you know, the height of this. Okay, I guess what is the height defined as? Number of edges in the longest simple path from the root to the, okay, so here there's 1 edge, 2 edge, right? Here there's 1 edge, 2 edge, 3 edges, right? So it's like here it's like, oh, my left kid, you know, has a height of 1. And my right kid has a height of, so a leaf node has a height of 0. Usually I say like, you know, none has a value of 0. But like some people like to say like, you know, a none node has a height of -1. And then like, you know, a leaf node has a height of 0. And so I don't know. My usual personal preference is to just deal with things in terms of a leaf node, you know, has a height of 1 and so on. But okay, in this case, leaf nodes have a height of 0. So yeah, this has a height of 1, which again, like I usually like the height being the number of nodes in the path, right? Not the number of edges, but oh well. And then here, this has a height of 3 edges. And then it's like, yeah, so here it's like height of 2, height of 3. But then if I delete this guy, then the right side actually now has a height of 0, right? So it's like all of these nodes, if anything, these nodes, I can also, are all the values unique? Yeah, okay, all the values in the trees are unique. So that's very interesting. So if anything, I can actually be like super lazy, right? Where it's like if I get a query and at any point I visit a node that's been deleted, I know everything inside of that subtree is deleted anyways, right? So if anything, I don't even have to mark 6, 5, and 7 as deleted, right? I just tell you like, yo, my height here is 0. Or I tell you, if anything, I set the height to like -1, right? And it's like, oh my goodness, don't go here. This is a deleted node. Ooh, so maybe I can get away with not even doing, like being lazy, right? Where it's like, if I delete the subtree at 4, I don't even quote unquote delete 6, 5, and 7, right? I essentially put a big X here on the 4 saying it's deleted. And that way it's like, if I ever try to go here, it's like, not allowed. Everything in here is deleted, right? Even though I actually didn't delete the 6, 5, and 7 and so on because I'm too lazy. And any computational work that I can save is going to be really good in this problem, especially when you know like n times m is too slow of a solution. So I need anything that I can save in terms of computational cost. Also, okay, I got to remember I got to leave in at most an hour from now for the concert, at most. So I got to try to do this, you know, not too slowly. Okay, so we've populated the parents, you know. Self dot is deleted is equal to a set, actually, right? We're gonna put deleted nodes inside of there. Okay, another thing I can do populate parents and heights. Okay, well, actually, we'll just do populate parents. And here we'll do self.populate heights. You know, 2n is still O of n. Right, 2 times 10 to the 5, yeah, I'm getting into, you know, annoying little territory, but 2 times 10 to the 5 is okay amount of work, right? So here we'll do root, and then here we'll say, actually, we just need to do that, right? So here we'll do def self dot, actually, this needs to no longer be vals. These point to nodes now. In fact, I'll comment that out. Self.parent of root is equal to parents, and there you go. So now these are nodes that point to nodes instead of values that point to values, even though values are unique. Actually, that's very interesting, right? Maybe I could do something like that. Where it's like, you know, I end up saving a little bit unspaced. Asymptotically, no, but like, you know, it's better to store an int than it is to store an entire tree node that contains an int inside of it. But usually in these types of problems, space is not the issue and time is the issue. Okay. Self.populate parents. No. Self dot. Goodness me. Def populate heights. Self, comma root. Right? Here, if not root, return. Actually, we can do if not root, then return -1, right? Because here, what we'll do is the height will be, you know, get the height of the left child, get the height of the right child, take the maximum of those, and then add 1, right? And if we want a leaf node to be of height 0, right? Well, then its left child will be none, which will return a height of -1. This will return a height of -1, and then, like, or here, like -1, -1. And then it's like, okay, the max height between my two children is -1. -1 plus 1 equals to 0. That way we give a leaf node a height of 0. So here, if not root, we're actually going to return, -1. Actually, we don't even want to return stuff here, right? You know what? Self.height is equal to this. We'll give none a height of -1. There we go. That way it's like, but the very same argument. That way, leaf node equals max of -1, comma -1 plus 1 equals 0 as wanted. Height equals, there you go. Nice. So if not root, then this. Yeah, if not root, then this. Then we'll say, okay. Maybe it's like, you know, we do a get height function. Okay, maybe we do, you know, like def get height, self, comma root. And then it's like here, it's like, you know, if root in self.height, return self.height of root, right? Otherwise, we do left is equal to self.get height of root.left, right, you know, left height, right height, self.get height root.right. And what's good is that we have none as -1, right? So this is good. This is good. Height is equal to max of left height, comma right height, plus 1. Self.height of root is equal to height, return height. And that way we recursively populate everything, right? Here we'll do root.val, root.val, root.val. Here we'll say, you know, self.get height of root. And here not print the self.parent, but print self.height. If not root, return -1. There we go, whatever. Yeah, okay. So 2 has a height of 0. Good. 3 has a height of 1. Good. 6 has a height of 0. Good. 7 has a height of 0. Good. 5 a height of 1. 4 a height of 2. 1 a height of 3. Perfect. Okay, so we have done this perfectly. Now we will get rid of this. We will map nodes to heights, not values to heights. We could map values to heights and it would make things easier to debug, but for now we'll just do the whole. We know that we can do that just because everything is unique, right? Left height, yeah, okay. Populates all the heights. Using memoization. There we go. With memoization. Or via memoization. Okay, that's good. Okay, very, very nice. Again, I gotta make sure that I don't spend too much time on this problem. So now we have all the nodes' heights and their daddies. That's good. So that way, whenever we delete a node, we know, yeah. So now it's like, okay, here we're gonna do def delete subtree. Given a root, right? Here, we'll have another helper that, you know, like finds the actual value. Oh, but the only thing, actually, we could also map all the numbers to their node, right? That's not so bad. Do we do another parsing? Yeah, so this can go. The thing is, I can probably sneak it in there, one of them. Also map val to node values for easy lookups later on, right? Because queries is a number, right? We want to map a number to the node we want to delete. So self dot num to node of root for easy query lookups later on. This breaks S in solid. Please don't murder me, Rawad. For context, Rawad, he was my software design teacher, or professor, I should say, at the University of Toronto, and I TA'd for him like 3 times. And so yeah, I teach solid like all the time at school, because we were like, you know, learning in Java and object-oriented programming and so on. It's like, yeah, the proper way of doing this is, you know, separate the responsibilities. Here, this function is doing 2 things. That's not good, but hey, this is LeetCode. This is not production-ready code, so I can get away with a few, you know, code smells up in there. Okay, sorry, my eyes hurt a little bit. Oh, whoa, okay. Root.val, ow. Oh, sorry, my eyes. Forgive me for that. Oh my goodness. Okay, maybe I turned the brightness a little down. Oh, my eyes. Sorry, I'm really sorry for that. Okay. Let's just keep going. Is equal to root self.num to node. Ouch. Okay. I'll fight through this. Sorry. Self.num to node of root.val. Yeah, it's equal to root. So now we have that. Yeah. So self dot num to node mappings is equal to this. So now I want to do print self dot num to node. Root of val. So 1 maps to 1, 3 to 3, 2 to 2, 4 to 4, 6 to 3. Yeah, okay, so this is perfect. This is perfect. This is perfect. Okay, so now we can get height, we can get populate parents and so on. At this point, we now have access to O1 lookups of node to height to value to node 3 node to parent node. And okay, and now the next thing we want to do is def delete subtree at a specific root. Right? In that case, we're just going to say self.deleted. First of all, assert root not in self.deleted. Be lazy and do not waste time trying also, will I ever get a query to delete something that's already deleted? Is that possible? If I delete 3, 2, oh, I can get something to delete something that's already been deleted. Okay, so when I delete a node, do not waste time trying to delete subtree, and do not waste time trying to delete subtree. Oh, sorry. Be lazy and do not waste time trying to delete subtree. From current node. But sounds good. Later on, when okay, later on, when deleting another node, it could have been a node we wanted to already delete. So we should check each time if any of its parents have already been deleted. If so, we can mark this node as deleted, as well as any node along its path if we so choose, and return the same height that was returned in the previous iteration. Bless you, baby. I.e. at answer of -1. Sorry. Okay. Okay. It's not going to be too trivial. And I got to make sure that I do this as quickly as I can. Assert root is not in self.deleted. Okay, we'll put a space here. And yeah, here we'll mark step 1, mark node as deleted. Self.deleted.add root. Here we'll do node. Then, yeah, no, we don't want to waste time, quote unquote, just going down the whole tree of children and deleting them and so on, because we might not have to query them again and so on. So we only want to lazily update, deleted nodes as we need to, right? I always try to do the least amount of work possible and still have a correct solution. especially for a problem like this where it's probably going to be very, very useful, right? I.e., like, you know, the trivial way of implementing this is going to be very simple, right? Just each query, like, keep deleting that from the tree and so on, blah, 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 and then, you know, return your answer every single time and, you know, calculate the height every single time. But worst case, that's going to be very super inefficient. It's like going to be O of mn up to their level complexities, right? Even though, you know, the tree keeps getting smaller and smaller, they can put a test case where they screw you and make you time limit exceed it. So I don't even want to try that, especially since I'm on a time limit here and I need to make sure that I solve this within the next 30 minutes. That's my mistake that I do with the contests, where I try question 4 and then I'm like, oh, let's do the simple way. Of course it's CLEs and so on. I'm like, you know what, I don't want to do those types of attempts anymore. Okay. Mark node is deleted. Yeah, so node is marked as deleted. That's cool. Then, yeah, we're not going to waste time deleting its children. But now we'll do self.heights of node. Here we'll have a def. Actually, we'll have a def is deleted, right? Now here, okay, we'll call get height. Yeah, okay. Populate heights. There we go. Def is deleted, self from a root. Return node in self dot deleted. So here we'll do assert not self dot is deleted node. Okay, we'll just have that function in there. Here we'll have a get height function, right? Def get height self and a node, right? Left height equals 0, right height equals 0. If not, when you get the height of a node, okay, we gotta make sure when we delete nodes, actually, yeah. You'll add none, right? None is always deleted. Where am I writing my current code? Node.left. Actually, none already has a height. Left height self.get height of node.left. If the tree is deleted, right? If there's no tree, there are no edges alongside that path, right? But yeah, if it's no, I gotta relax. I should return -1, right? These should be -1s. Okay, if I delete, like, you know, this 9, right? The height on the right of 5 should effectively be made -1. That way, if they're both -1, I take the max of those two, add 1, and this is, you know, of height 0 because it is the root happens to be a leaf, and this is good, right? So left. Actually, yeah. No. Height of node.left. Yeah, left height is equal to this. If not, self dot is deleted. Node.right. Right height equals self dot height of node.right. Only query left height. Node height if it hasn't been deleted. And same thing for the right. Return max of left height plus comma right height plus 1. Okay, the important part now is that get height is now an O of 1 function, right? If the node is deleted, then like, bro, this thing does not have height, right? So like, if it's been deleted, right, which I do by adding inside of my, you know, my set here, if it's been deleted, then it's gonna have an effective height of -1, right? So if it is self-deleted, this is as -1, right? Okay, in worst case, you know, the root happens to be a leaf node, in which case this is -1, max of -1 is gonna be -1, plus 1 is gonna be equal to 0, and there we go, the root has a height of 0 in case it is a leaf node. So it works out really nicely in that way. Okay, so now we have a get height function that is O of 1. That is perfect. So we can always query the height of the root node, right? If we delete the two subtrees, you know, to the to the left, that scared me, to the left of the and right to the root node, then GG, the height is always 1 until we delete the root, bro. So there you go. So now get height is O of 1. The only problem, okay, actually, we're very close. We're very close. I'm gonna do this within my time limit. We're very close. I know what I need to do. We have get height now. Yeah, we have self to delete subtree, right? So node. The only annoying thing is search. No. We don't have to search. Again, I have all the values to their nodes. This is absolutely brilliant. This is absolutely brilliant. Okay. So here, delete subtree. Mark. Yeah. I'm gonna call this mark deleted. Now tree queries. Okay. Now we're gonna do for query. Okay. We're gonna have an answer. All right, right? And that's what we're gonna return at the very end. Actually, we might as well do this. Self.answer is equal to an empty array, right? And here we'll do return self.answer, right? In case we need answer inside of our calls, right? Because we might need an answer of -1. Or actually, we don't, right? We always call the root of the height of the root no matter what, because again, get height is now an O of 1 running time complexity algorithm. Okay, this is good. So we actually don't need this, and we could do this. We don't need this, and we could just do this. Return answer. Okay. Now for query inquiries, right? Okay. For query inquiries, okay, this is good. If this was a normal LeetCode hard, I'd be like, oh, okay, let's take our time, let's big chilling and so on. But now that I have, like, you know, this 20 to 30 minute, like, let's go, finish this timer in my head, it's like, it makes it a whole lot scary, right? It makes it feel like an interview problem. If so, maybe I should, you know, start putting a timer on the LeetCode problems, not just so that, like, you know, I don't waste a lot of time, but so that it gives me that, you know, panic, button inside of my heart. Like, my heart is racing right now, trying to make sure that I get this done in time, because it's like, I can't just explore possibilities and take my sweet time. It's like, no, I have to try to, you know, get to the answer not only correctly, but as fast as possible too. So it brings a whole new dynamic to solving this problem. So, okay, for query inquiries, yeah, okay. So the very first thing we need to do, yeah, so we'll do, you know, for I in range length queries, val to delete, or val is equal to queries of I. You know, we do for file inquiries. Self dot mark oh to do. Okay, actually we're gonna update the self dot is deleted function, right? If node and self dot deleted, return true. Ooh. Wait, we can never ever delete the root value, right? Okay. Disclaimer. Important. Since we are never allowed to delete the root node in this problem, we know the value for the root node will never change. We can use this as an identifier. Actually, what am I talking about? I set the parent of the root to be equal to none anyways, right? Self.populate parents. What am I talking about? Yeah, root and parents, right? Set of root, bro. Okay, get height. Populate heights. Dude. Yeah, I give it a value of, yeah, okay, it's deleted. While node. Okay, we'll do root. Node. If node in self.deleted, path is equal to this. Okay. If node isn't self.deleted, return true. Okay. That's the base case, whatever. Path is equal to just node. Mark all nodes in path as deleted first. Deleted node in path. Self.mark deleted of path node. Path node, right? So I have a mark deleted function. Cool. If node in self.deleted, then yeah. And then return true, right? Then return true. Otherwise, our loop invariant is that node is equal to self dot. Here we'll have a def get parent self comma node. Node in self dot parent dot parent of node. There we go. Dot get parent of node. Well, node is not none, right? Because eventually node will become none. since none is parent of root. And here return false, right? If we reach the root and nothing has been deleted inside the path, it is not deleted, right? So there we go. We don't even need that base case, but whatever. I will keep it because why not? So now we have a reliable is deleted function, right? Even though I do not lazily delete the stuff, it is reliable. Okay. This is beautiful. This is beautiful. This is absolutely beautiful for val inquiries. If self.is deleted, node is equal to self.num to node val. Assert val in self.num to node. Here we'll just say, def get node from val, self comma val, assert val in self.num to node, return self.num to node of val. Okay, there we go. And so now we'll just do node is equal to self.get node from val of val. There we go. Okay. So now we have gotten the node. If the node is deleted, answer.append answer is equal to self.get height of the root node, right? Root answer.append answer, right? And then continue. Otherwise, if it is not deleted, right, then what do? We mark it deleted. Oh man, I also really need to use the restroom. This is terrible. Yeah, if I mark it as deleted, yeah, I can mark it as deleted, right? I can just mark it as deleted. Else, wait. If not, self.is deleted node. Self.mark deleted of node. And then this stuff in here. Get rid of this, get rid of this, get rid of this. So what happens if I run something like this, first of all? That's weird. So I pass this case. I don't pass this case. So here, when I delete a node, I need to update all the parents' heights. Okay, here we'll do def delete node self comma node. Firstly, mark node as deleted. Self dot mark deleted. Where's the third case, right? Here we'll do self dot to do update this maybe. I'm not gonna be able to solve this in time, am I? This sucks. This sucks. Okay. If not, I know what to do. It's just I need the time for it. That's a bummer. Node is equal to yes. Deleted. The node. And then it's like okay, update this dude's. self dot get parent, right? I have a get parent function of node. Self dot height of parent while parents loop invariant node is equal to parent, right? And here we'll say parent is equal to self dot get parent of node. Self dot height of parent is equal to self dot get height of the parent, which will now be dynamic, right? The get height function. Yeah, I need to update all the parents' heights. I cannot delete a node that, you know, where it's like further up the chain is deleted already, right? While node, parent node, then here's like, you know, return. The height of parent equals self dot get height of parent. Yeah, okay, there we go. So that way I don't mess with the none. Right, okay, so now I do self dot delete node. Still wrong, eh? So why? Here delete 3, then I delete 2. One, two. But what the hell? Yeah, removing the subtree is 2. Wait, are you joking? Wait, so when we delete a subtree with a query, that subtree is not deleted for the rest of the problem? Is that a joke? What? There's no way. I thought it was always deleted. Like you deleted a subtree, so it's forever deleted. Oh, that's annoying. Wait, if anything, that just makes this problem easier because now you just have to think in terms of height and so on. But that's so frustrating. Why the heck is it a temporary delete? You're given the root of a binary tree. Each node is assigned a unique value. Yeah, after performing only the ith query? I thought it's like, you know, if you perform the ith query, you've performed, you know, query 1, query 2, and all the way up to query I, so you've deleted that many trees. Yeah, okay, the queries are independent, so the tree returns to its initial state after each query. I completely missed that. I thought that, you know, it's like you delete at the first query. That's permanent delete. Okay. Well, this just makes the problem even easier. This just makes the problem even easier. All the queries are independent of one another. You don't have to care about the modified state of the tree. It's just, there you go. So it's like, you know, you keep track of like, you know, self.og heights. Nah, bro. Oh my goodness. You know, maybe like I just keep track of self.temp heights. But now I definitely just don't have enough time by the time that I get to the concert to finish the rest of this problem. No! Oh, that's frustrating. Because it makes the problem easier, but I don't have time to solve it and explain it in the next 10 minutes. There's just no way. That's a bummer. Big bummer. Let alone upload the entire video. Okay, yeah. There's just no way on earth this all gets uploaded by the time that I leave anyways. Okay. Hello, I see. Okay. Yeah, I'm okay. So I completely okay, I see. Okay. Man, I completely misread the problem, but the problem is it's just an easier version of the problem that I was solving. Well, okay, maybe I'm getting, a little arrogant here, so maybe I shouldn't. But like here, you don't even have to keep track of state, and I was trying to keep track. Like I didn't want to, like delete that part of the tree every single time and so on, because I was like, maybe we should like not do that work if we don't have to, and trying to be clever and so on. Here, there's no cleverness, right? You create a temporary copy of the heights every single time. That's of n work every time, so you can't do a copy of the heights, right? But you revert the original heights. You keep track of the heights in that path, right? And then you fix up that path once you're done with it. Right? So it's like you create a new map of like, temp heights. And if something is in temp heights, that's its actual height for now, right? And then once you're done with temp heights for one iteration, for one query, you clear that thing. Just, man, that's just such a bummer. Okay. Yeah. Of course it's not gonna be deleted. This is the only node we delete. It's the only node we delete. Okay, for valid queries, just okay. Self.temp heights is equal to this. We clear it. Clear it first for every query. Here we'll do self.temp heights. Temp heights. Temp heights. Temp height. And we'll still just do node is -1, whatever. Here we'll do self.temp height of node. It's been deleted, right? So it'll be -1. Same as node. Parent is equal to self.get parent of node. While parent is equal to self.temp height of parent. There's left and right? Left if parent.left in temp height in self temp height else self.height parent.left. Same thing for right? Right height is equal to this parent.right. Parent.right is in the temp height else I don't care that it's long right now. Height is equal to max of left height, right height plus 1. Self.temp height of parent is equal to what is it equal to? And can we redo the same query again? Are all the queries unique? Because if they're not, then I can cache them. It's like, why would they give me why would they give me duplicate queries, right? That's an easy fix. So like whatever. Self the temp apparent is equal to, first of all, loop invariant. Parent is equal to self.get parent is equal to height. Right? Assert root in self.temp height and ser.append self.temp height of root. Return answer. Something like this. Yeah, okay, this is just an easier version of the problem that I was solving. But maybe now we time limit exceeded, right? Okay. So we can't just do m log n work. Time limit exceeded. Jeez, okay. Actually, okay, one thing we can do is cache results, because any parent we delete, we will have known the value for these cases, right? Cache is equal to this. Right, deleting any single node inside of that parent chain will have the same effect. Oh, yeah. Okay. Eval in cache. Turn cache. Answer.append cache of val. Continue. Right, and here we'll do, first of all, cache of val is equal to self.temp height of root. Right, so something like this still works, right? Right. What? Oh yeah. Whoops. There we go. There we go. Sorry. But yeah, so something like that. There we go. Here we'll have a path is equal to this. Path.append parent. And yeah, for node in path, we'll do cache of node.val. Here we'll start it off with node. For path node in path. Okay, this guy, answer is equal to this guy, right? That way we just append answer, and we append answer to here every single time. Now we do this. Is equal to node.val. Actually, yeah. For node val in path, cache of node val is equal to answer. Here we'll do node.value. That add parent.val. Oh. There we go, sure. Ooh, okay, maybe I don't include node. Okay, so is it not always the case that if I delete, or is it maybe its children? Its children that are the ones? where it has the same effect? It's like if I delete a node. No, it's not always the same case for the parents. But there's some idea like that, right? Where it's like as you go up along the tree, there is an ability to cache some stuff. Okay, I will leave the problem here. Again, we're at a point, I'll leave it at a point where we're time limit exceeding. Actually, I'll leave this stuff in here. I'll put this as commented out. I'll put this as commented out. Put anything with cache commented out. Right? I'll run this. Submit this, and here ideally we time limit exceeded. Okay, so the point is I've been thinking about a completely wrong problem this entire time, which is a big bummer. And yeah, okay, so we time limit exceeded, so okay. I will now have to go to the concert, so this means that I have to stop the problem here and I'll have to come back later into it. The big bummer is that, again, like I completely misunderstood the problem and I didn't realize this part of the problem. I thought that once you did a query, it was a permanent query, right? And not a temporary one, right? I thought that like after performing the ith query means like, oh, you've already performed query 1, query 2, all the way up to query I, not inclusive, and now you're performing query I and then return the height and so on, right? I didn't realize that every single query is independent. So it's like a completely different problem that I'm trying to solve, and of course I wasn't going to be able to solve it in just a 10-minute time period. So that's a little bit of a bummer. But okay, so for now, I will just be right back. So for you guys, it will be 1 second. I'm gonna go do to the concert. I might do some other stuff. It might even be the next morning by the time that I'm finishing this problem and so on. So don't worry. For you guys, it'll be instantaneous. For me, it'll be a few hours, if not a full day. Yeah, so for you guys, just see you in literally just 1 second. Okay, hey there, I'm back. Let's get straight back into this problem. So what was this again? You're given the root of a tree and nodes. You're given m queries. Yeah, they're independent. Oh yeah, remove the subtree at queries of I. Answer of I is the height of the tree after performing the ith query. The queries are independent, so tree returns the initial state, height. Yeah, okay, I remember this. And we had a wrong solution because I thought that the queries were not independent, right? And so then we came up with a solution that works, but time limit exceeds, yeah. Okay, I don't have the, the complete full context idea of what I wanted to try when I left the video before the concert and everything, but I should be able to get back on my feet really quickly as to where I left off, right? So here I wanted to do some caching, right? Okay, so I gotta think in terms of, yeah, if I delete a subtree, okay, let's think. If I delete a subtree, who do I affect? I affect my parents, right? If this guy's height was determined based off of this guy, then this guy's height will change. And then the one above that, maybe its height also changed, right? Oh, but then I can, okay. But then I stop, right? Ooh. Actually, yeah, we can do something like that. Okay, so here it was like while parent, left height is equal to self that temp height parent that left, blah, 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 blah. Yeah, so we just deleted node. If height is equal to self.height of parent, if no change, then there will be no further change two remaining parents either, so can break out of the loop here. Then we break out of the loop. And then here, we don't do this. Answer equals self.temp height of root if root in self.temp height, else self.height of root. Answer that append ants. Does something like that work? It does, at least for these cases. And what if I use this test case in here? Do I pass this test case now? Still a little slow, but at least I'll cut off work wherever it needs to be cut off, right? I guess it might still be too slow. Yeah, so it's still TLE. So that's the problem. Even though, yeah, even though I break whenever, okay. So that's interesting, right? I break as soon as I need to stop checking. So it's like we really have to internalize what it means to delete a subtree, right? If I delete a subtree, then I affect the parent's node height. Oh, but maybe I cache results. Yeah, maybe I have my cache in here. Okay, yeah. Maybe I cache results. That way, if I ever get to that as a parent again, I already know the answer. I have to really internalize, right? So if I delete here, and then it's like I delete 5, right? And then let's change this guy's. But I only know this guy's answer when it's deleted, not necessarily when it's this. This sucks. I really would have thought that, like, going through up the parents chain would have worked. Right? For val queries, like here we just return this. We don't time limit exceed here, right? Right, here we don't time limit exceed. So it's this part. For val queries, clear the temp heights. Yeah. Maybe I do have my cache. Val. Cache of val is equal to ants. Yeah, but for something like this, it's just not, it's too slow still, right? It's just, yeah, the thing that's annoying is that getting the height isn't necessarily log n if the tree is not balanced, but we gotta preserve the way that the tree is, right? Like I can't use like an AVL tree where it's like, you know, this, I rotate this where like 1 becomes a child of 3 and everything. I just cannot do stuff like that. Yeah. So how does it, if I delete 4, like if I delete 7, right? It's like, oh, I just messed up 5. Which means I might mess up 4, which means I might mess up 1. It's like, and you keep going as long as I mess stuff up, or until I know I get to the point where it's like it didn't affect things, right? Or it's like, you know, roots left. You know, roots left is length 2, so once I get to, you know, like less than length 2 and know how to stop, that's also a stopping criteria. Like, what do I have? I have all of the nodes' original heights, a mapping of all the values to nodes, and all the nodes to their parent node. So if I want to delete a subtree, okay, whoops. If I delete a subtree, okay, I always care about the height from root, right? I can also keep track of if a subtree, is in the left or right of root, right? Okay, I populate parents, populate heights. Oh, man. Do I populate all the heights as well as the height, you know, if I deleted that node? No, that's too many cases. I gotta think here. If I delete a subtree, okay, I could also think, is it in the left or right of the original root? If it's in the left, then, you know, I at most affected things by this much of a height. So it's like, you know, if I delete 4, which is a height of 3, then it's like, okay, I just take whatever was on the right of root minus that value, right? Is it something that simple? For LeetCode hard, probably not. Try it, you say? Okay, well, my girlfriend says try it, so you know what? Let's try it. Okay, maybe she's right. Let's see. Okay, let's try it. So you know what? It will be the very basic idea of, you know, figure out if, first of all, if a subtree is on the left or right of root. Only nodes are to the left. So I root that left subtree. Okay, def populate left nodes self. Left root. Root return self dot left node dot add left root self dot this left root dot left self dot this of left root dot right, and then return. Here we'll do self dot populate left nodes root dot left. Only includes nodes in the left subtree. Then here we'll do okay. Is left function that returns true and only if node belongs inside root dot left subtree. If and only if. Def is left of self comma node. Turn node in self dot left node. There we go. Okay. Now we're gonna do for val inquiries. Same thing here. Answer is equal to this. For val inquiries, we're gonna say left height self dot get height of root. Right height is equal to self dot get height of root dot right. So this will be root dot left. Then we do if self dot is left node is equal to get node from val. Is left node left height minus or equal to height is equal to self dot get self dot height self dot height. Right, this is how I do things. Yes. Height of node. Height. We'll call this node height. Else right height minus or equal to node height. Then we'll just say height is equal to max of left height comma right height plus 1, and we add dot append height and then return answer. So I don't know if something like this will work, so let's just check. Root is not defined. How is root not defined? Yes. Right, so here we have a wrong answer. Jeez, an incredibly wrong answer. Okay, so let's just have these 3 test cases in here just to make things go fast. So now we fail this guy. Can we not see like the tree that these things build? Okay. 105. So this will be, oops, okay. There's so much code. It's like 1, no 5. Well, no, can't have any trees, so this will be 3, nothing. 2 and 4, I'm guessing, is how this tree is. Something like this. I'll delete this, and the height is, yeah, 1. So here's like what? I put 2. Why am I putting 2? If I delete 4, 2, or 4, then yeah, the height here is 3, right? The problem is, okay, if I deleted 5, the height should be 0. Why is it not 0? So it's always a right node. So yeah, so the right height, 1, 2, that's 2. F string of node equals, node.val equals, node height equals, and self dot is left node equals, as well as print of F string, you know, left height equals, and right height equals, and then print, you know. So 3 has a height of 1. Yeah, but really it's like 1, 2, 3. It's technically just a height of 1. But that's like, you know, if you deleted both of these nodes, it shouldn't have 0 effect. Plus 1 maybe here? No. No. We'll create a function here called def is leaf self comma node return node and not node dot left and not node dot right. Right? So here where was I? Literally, where was I? Okay, line 60. Okay. Not self dot is leaf of node height plus or equal to 1. Okay, so that works. Wrong answer. Right, of course. Well, this one we get the tree. 1, 4. So what happens if we run this? Two, 1, 2. 1, 4, 3, 4. It's like it depends. It's like this is what I mean by like I'd love to go up to the parent every single time. Is there a way to do this more efficiently? Like it's clearly going up through the parents is too much time complexity. I have to know the heights no matter what, at least some way at some point, so that I can get the new heights efficiently. It's just the only way I can think of is once you delete a subtree, you go through its parents, right? Unless it's like, we apply the idea that we're trying now, which is like, delete the length of the subtree that you just deleted, because that'll affect the new height, right? Right, just keep going up until you stop affecting things. But that's what we tried, and that doesn't work. Okay, I gotta think, right? If I delete... Oh, no. There's no deleting the subtree in the middle. Once I delete a subtree, that height is gone forever. So yeah, deleting this, which had 2 nodes in it, only affected the height by 1. So really we should look at the parent. And then from that parent decide what happened. Yeah, the change in height of the parent is the change in height in total for that one. Okay, maybe this idea still works, it's just we're implementing it wrongly. Right, now height is equal to this. Parent is equal to self.getParent of node. Node.left if node is not equal to parent.left, else self.height by sibling is equal to parent.left if node doesn't equal parent.left, else parent.right. Parent height, self.height, or it'll be the sibling's height plus 1. Diff is equal to parent height minus of self.height of parent minus parent height. Total loss in height. Parent is equal to root answer.append Otherwise, there we go. Self that is left of the parent. Left, yeah. Here what we'll do is, if self dot is left the parent, then we do left height minus or equal to diff. Else right height minus or equal to diff. And there we go. Oh, okay, that worked. Wrong answer, okay. Yeah, so it's not that easy. I can't get away with cheap tricks. Yeah. Yeah, if I run this, how far off am I? $57. It's like, again, it's like I'd like to only have to go up to the parent as much as I need to. It's like, do I need to cache results? Like node and height pairs, maybe? Just why is it TLE? It's also midnight, oh goodness. Okay. Doing a perfect binary tree is just like log n time, and that's completely fine. Yeah, but worst case is like, you know, you have an infinite chain. This is really frustrating. If I do something like this, they all work. But then it's too slow. Damn it, I really thought that something like this would not have been too slow. Yeah. Just dang. Each node is assigned a value. Like, surely we've got to be able to do something clever. Like, what can we do? A deleted subtree, it's like, yeah, I directly affected that parent. The difference in height loss in that parent. I only affect the one that it affected. Jeez. Yeah, this is fine. I even check which subtree it belongs to. Unknown, bro, please. Yeah, it's just a bummer. What is going on? Like if I delete some tree like this, if I delete 7, right? That's like, oh, uh-oh, I affected 5. So does that mean that, like, I'm like, wow, I affected 5. So then get this guy's height. But then, yeah, it's like, go all the way up to the parent. Like, I'm so sick of this, bro. Why is this TLE? Yeah, because worst case, they give me a tree that's like, completely one straight line. And I die because it's m times n in that case instead of m log n. This is just wild. Wild. Like if I delete 5 here, if I delete this whole subtree at 5, it's like I know how to update this guy, which means I know how to update its parent, and I keep updating them until I don't have to anymore, I reach the root. It's like, how is that too slow? Like, what else can you do? Right? Like, like it's like with heaps or anything, it's like percolating. It's like you have to go up to the parent. How do you not go up to the parent and figure out the answer? How do you do it? Does this problem have any hints? Okay, let's do hints. Let's just look at the hints. It's late and I'm running out of ideas, so let's just look. Okay, let's check out hint 1. Try pre-computing the answer for each node from 1 to n. What? Try pre-computing the answer for each node from 1 to n. Answer each query in O of 1. Okay, so if we cache results, that essentially gets rid of that problem. What? We've tried caching. Instead of pre-compute and so on, just compute on the fly, and if you've seen it before, then yeah, we've tried caching, right? So here we cache it, right? Cache, yeah, so here we have caching. Maybe I try this path idea again. Maybe I cache pairs. This is interesting. Okay, I don't even want to open hint 2. That's an interesting idea. Try pre-computing the answer for each node from 1 to n, because there's n nodes, and then answer each query in O of 1. Self.ans. For each I, 1 less than or equal to I less than or equal to n. Okay, interesting. So here we have this self dot populate answers for I in range 1 and n inclusive. Answer of I. This is interesting, right? Is equal to self dot get modified height of I. And here we just take this idea. But then again, that's just what my cache does. Like here I'm just pre-computing all the i's. Here I'm just saying, like, you know, oh no. Okay, wait, I had the cache up here at the bottom. I wasn't caching up there. Wait, is that literally it? Here, let's have a cache is equal to this. Cache of val is equal to height. No, I'm getting wrong answers, not TLE-ings. Okay, so maybe we get rid of this solution. Right? Yeah, if val is in cache, we've solved this problem before, then GG. It's gonna be a nightmare. Okay, maybe there's just a way of doing this efficiently, right? Try pre-computing the answer for each node from 1 to n. Obviously, if I do them all individually, it's just not gonna work, because that's essentially what I'm doing. Is just, instead of doing, like, you know, this is like bottom up DP kind of mindset. My solution is like top down DP kind of mindset, where it's like, you know, I solve as I go, and then if I've already solved it and I try to resolve it again, just look up in my cache and return that value. So here they're pre-computing, but they're doing something smart. Like get height. Right, okay, so if I have a node and I'm like, I'm gonna get my heights. Ooh. Maybe that's how it is. Maybe that's what I'm missing. It's like caching, but you do it giga efficiently. You solve all n problems, because solving all n problems at once helps you do them all, but in an efficient way. That way, even if you have a query for every single thing, still reasonably efficient. That's actually very intelligent. Okay, I can see why that helps. Populate answers, comma root, right? So idea. So yeah, if not root, return. I can't delete the root. Oh my goodness. So from here, it's like, if I delete left child, so it's just right child's height plus 1. vice versa for deleting right child. There's no way it's this simple. Oh my goodness. Answer is just right child's height plus 1. So if root dot left self dot answer for root dot left dot val, which is equal to, if I delete that, is equal to okay, if, oh my goodness, I'm close. Okay. Self dot answer of root dot left okay, if not root dot left, not root dot right, return. Doesn't make sense to delete yourself. It's not necessarily 0, right? Oh my goodness. I have to think about this. I have to really think about this. Okay, let's solve this case. Solve the answer of root dot left. If I delete root dot left, oh my goodness. It's not that simple, right? Maybe it's like I pass in, like, you know, an effect subtractor. Like the more deep the node is, the less important that value is. Man, I hate this. Okay. Okay, let's also open up hint 2. Let's just open up hint 2. Let's open up hint 2. The answers can be predicted in a single tree traversal after computing the height of each subtree. Damn, okay. So maybe we do need the heights first. Okay, so we have the heights. In a singular traversal after computing the, okay, so that means, so okay, the hint essentially is use that height parameter. Well, of course, right? I was gonna do self dot height of root dot right, you know, here plus 1. Right, I was gonna use those heights anyways. Maybe this isn't as helpful as I thought. Okay. Okay, we're somewhat close in ideas here. No, this is correct. Or if root dot left, then this. If root dot right, then this. Actually, there we go. And here we do self dot. Where am I? What? Okay. Root dot left. Self dot populate answers of root dot right. And here maybe we do vals. Is it as simple as this? Self.ans, is that what I've called it? Turn none. Deleting 4 gives me a result of 2. That was the expected. Here it's 3, 2, 4, 8. 3 gives me 1. But 3 maps to 3. Okay, I'm not doing this right. If root dot left, yeah, this is the answer. If I delete this guy, wait, this is not quite right. Right, yeah. It should be add distance from root to node as well. Add distance root to node as well. So here we'll have a depth, maybe is equal to 0. Here we'll have a depth plus 1, a depth plus 1. And here we do plus depth. Plus depth. Does something like this work? Four still maps to 2. 3 maps to 2, which is bad. But what about 2? Does 2 map to 1? 2 maps to 2, bro. What is going on? Okay. Like if I start at a depth of 1, or you know, it's actually okay. Let's make our life easy. Here, let's say okay, depth is equal to 0 at the beginning. We've got some cases working. Maybe here I do plus 0, and here I do 1. No. Yeah, the answer for deleting that left subtree plus the depth of root dot right. Yeah, okay. This should really be this, and then initial depth of 1. That is how it should be. That's like, why is this the outlier? Print ants. Yes. Three maps to 2. Test case 2. Yeah, what if it was none already? So maybe the none cases are messing me up? Maybe something like this? Or maybe it's the other way around. Definitely not the other way around. It's not it. Although that would make sense, right? It's like, that's one possible answer. Actually, here I should have a yeah, here I have an underestimate. Do I always have underestimates? Yeah, always underestimates, don't I? Underestimate. Under. Yeah, I always have underestimates. That makes sense. Like, this is one of two possible cases for the height. Maybe here I do an if is left. Yeah, I've populated the left nodes. One equals self dot height root dot right plus depth plus 1 plus depth. The depth will equal 0 initially. 1 plus depth. We'll here say OG root self.root equal to none. Self.root is equal to root. Root val. There we go. self.root.val. Right. Yeah, if this guy first of all, assert that self.isLeft of root.left is equal to self.isLeft of root.right. Case 2, if that guy's on the, yeah, is equal to root node.right self.height of root node.right. Case 2 is equal to self.height root node.left. Ants root.left.val for the max plus 1 plus 1 case 1 comma case 2. Root jeez, dude. Yeah, the very beginning of the splits, right? Ugh. Yeah, if root is left, right, case 1 is we look at the root.right. Gosh. Why can't I solve this? Try getting the answer from, yeah. Maybe it's not that difficult, right? The height of the roots for any subtree delete. Why is this so difficult? Just, I don't know. Don't know. It's also because it's late, and so I'm just having trouble thinking. The pre-computing the answer for each node from 1 to n and answer each query now of 1. We know that going up through the parents does not work because it is too slow. We know that. So I'm trying to think, like if you work your way up from the bottom, does that help? This is essentially what I'm trying to do here. Like if I delete my tree, again, it's the same problem I'm trying to, like the hints actually don't help much, right? Because like I was trying to catch and so on. It doesn't really answer anything. It's like still, what does it really mean to delete a subtree? Like how, like here they claim you can do each query in O1. How? Do you not have to go up to the parents and keep informing until it's not different anymore? Like, how do you skip this step? That's insane. If I delete 5, I need to tell 7. Oh, I messed. If I delete 7, I need to tell 5. Oh, I messed up 5. It's like, I need to tell 4. I messed up 4. But it's like, oh my goodness, I didn't change the. Oh no, I did change the height of 4. So in this case, I have to keep going. It's like, oh 1, your height did change. It's like, okay, there wasn't. Oh, this was the one that affected me. Then yes. It's just crazy. Accepted, but TLE's. Is it because I have to dispose the dictionary every time, and that's not cheap? Essentially, the hard part of the problem is like, how can I do them all at once? And because of the fact I'm doing all at once, it's efficient, right? Like for example, here they're basically telling you, right? It can be done in a single tree traversal after computing the height of each subtree. But it's like, you know, no, like of course, genius, like. But how? Like I wish I had a hint on the how. Ugh. Just because of the heights of everything, like I still need to inform the parent and the parent and the parent and the parent and the parent until I don't affect it anymore. equal to ants. Did nothing at the very beginning. Oh, yep. Sorry. This will be parent and this will be height. Something like this work. What? Bro. Oh, break. Yeah, that's my bad. Yeah, so that works. But is it efficient enough to get me to the finish line? Looks like no. Wrong answer even. That's wild. Actually, yeah. Is done is equal to true. Is done is equal to false. If is done, continue. Let's use that test case. Answer that append ants. Okay, so now these cases are good. Memory limit exceeded. Bro. I'm stuck. I'm very stuck. How do you do it? All of one time. It's just I don't know what to do. I don't know what to do. I say cap. It's 1 a.m. now. I can't keep going on with this forever. But I have to solve the daily each day. I wish I could solve this when I was less tired. I don't want to look at the editorial, but that's the only thing. But at 1 a.m. do I really have a choice? Because there's my girlfriend here in town for just 2 days. I'm already wasting too much time on this problem. Or do I just come back to this tomorrow? And then it's just like I'm taking away time from our time together tomorrow. Just this sucks. Oh yeah, the answer the query part is an O of n. Is an O of 1, yeah, because you've had the value. I have the height of each subtree, yes. But how do I use that? Like, bro. Okay, maybe I get the parent's height. What was I doing here? Populate answers. Maybe I get the parent's height. Right, if I delete the parent's height, or the other subtree from root. Self.root. Val is equal to self.root.val. Here we'll do a return. Self dot if left ends of root.left.val. Height of root.right plus 1. Root.right, self.ends root.right.val. Root.left plus 1. Populate answers. Plus 1. Populate answers. Plus 1. Right, okay. So root.val doesn't equal self.root.val. The root underscore val. Nice. Okay. So now we're not the root node. Thank God. Okay. Okay, now can we do something like this? You okay? Okay, just give me 1 second, guys. Okay, sorry about that. Where were we? Let me control Z maybe. Oh yeah, okay. Oh, we're retrying this idea, which means that we need to, there we go, this guy. Okay, how is this not possible, bro? Good. If I've already handled the yeah, from this guy, the answer should be left. The root case 2. Okay, I'm just trying to do this as quickly as I can. Oh, sorry guys. What? No, there's left. Equals 0. Actually, you know what? Okay, let's just do this. There we go. Turn it into thing. Okay, tired. Okay. I think that doesn't change right here. There we go, something like this. Form episode 2. Kill me. Like, actually kill me. Yeah. Bro, like, come on. Should not be -1 here. Right, the point is that like they recursively pass this left. For everything to the left of the original root, it's always true. There should be a 1. Dude. Maybe it's like, if I know what happens when I delete my parent. Why is this so hard even when I know the hints? Well, I mean, the hints I guess really didn't help clarify my main question. I already pre-computed all the heights, and I was essentially doing this via caching. It's just like, how do they do this? And a single tree traversal after computing all of the heights. But it's like we've tried every idea, right? We've tried, like, just subtracting the heights. We've tried trying to take this as literal as it gets. If you go through the parents, like, that's the correct solution, but it's TLE. My head is getting dizzy. It's a shame because I know I'm so close. Okay, I'm sorry guys. I think I just look at the editorial. Like, it's too late. My mind is failing me, and I'm just gonna stay here. Like, if I haven't solved it in the first 2 hours, I'm not gonna solve it from then on. So I'm not in the shape that I'm in right now. I could wait till tomorrow, but tomorrow I'm planning on maybe doing both LeetCode contests. I'll explain the reasonings once I upload those videos and so on. And I want to do stuff with my girlfriend while she's here. So I think it doesn't make sense for me to just struggle through this more. I would love to, and I would have loved doing this, if I was alone yesterday. So, but right now it does not make sense. So let's just look at the editorial, see how they did it. Left and right traversal, n plus q, approach 2, single traversal, approach 3, subtree size. Oh gosh. Eulerian Tor, jeez, n plus q. 2 largest cousins, oh my goodness. So much complexity here. Ha lol. No problem, 5 solution. Good job. Okay, let's look at approach 1. Yeah, brute force search. Try to trace height as we traverse from the root. The height after removing its subtree is simply the height of the tree before reaching that node. No way. Wait. Oh gosh. No way. So it's like, yeah, the order of traversal matters. Like the max height before I've reached this node is wild. But then it's like, what if the other one is very deeper, right? Okay. What the heck? Okay. Push 3. Yeah, okay. This is essentially what I was trying to do. If we know the index, we can remove this section from the maximum depth. Yeah, I know the depth, right? I know the depth and size. That's exactly what I know. That's what I'm doing. Okay, let's read approach 3 because this seems most like what we were trying to do. Interesting. Number of nodes, not the height? No, this is wild, guys. Okay, let's really try to understand. First approach. Brute force over processing, we're separately by moving subtree. Yeah, okay, but like if this branch is like, you know, super deep, it's like, you know, and you're like, you know, you're here, it's like, haha, if I was doing a BFS traversal, it's like, haha, the max height so far is 2, but no, bro, the max height was all this here. It doesn't matter that you got to this first. Unless it's like, you know, you go as deep left as you can and then right. But then, same thing. It's like when you get to this node, it's like max height was still over here. And why does my idea not work? Like, you know, either it's the depth and... If root dot left, right? I want root dot left. If I listen, if I delete, like, you know, do I have this messed up? Is this what's wrong? Hey, these guys are sure happy. Leaving node 2. You'll have 1, 2, 1, 2. I'm like, it is left, right? So it's like, am I dumb? Wait. No, if it's in the left, which it is, then yeah, root node dot right. This is unaffected. The height of this guy plus 1. 0, 1, 2. Yeah, this is 2. Then this dude, it's gonna be this is my current root, right? Root that left. Answer for this guy. This guy's answer 1 and 2 plus 0. So it should be 2 and 2. It's case 2 that's equal to 3? Why the heck is case 2 equal to 3? Simple 2. You done right. Oh gosh. Items. Print delimiter. Okay, 9. But 9 has a height of 1. Root node right. Is left equals, as well as the val equals. What? Why the heck is left false? Okay. Is left. Wait. Where's the root? Yeah, populate answers. Now maybe it's 2. Whoa. Okay. Everything except this guy, huh? Yeah. So now why is this guy wrong? No, this cannot be it though. We're making big progress. Oh, what do we have a failing case here? Yeah. He start as 1. These are underestimates. They're just bizarre. I don't get it. I don't get why it's wrong. Alright, if I delete root.left, right? Then the best height from that side is equal to the height of root.right, because root.left just got deleted. Add 1 to that, plus the depth to reach that node, right? And that's one path to get to it. Then the only other path, right, if this was on the left side, we get the right path from the root. And between these two cases, we get the best one. So why in tarnation is this not a correct answer? Print. Where is 57 even in this tree? I'd love to see 57. Seven 32. 7 is here. $55.20. 25.45. 30.45. 19.45. 30.48. 31. 22. Also, it's asking for the same guy over and over, like, why? Yeah. But this is crazy. How is this not correct? Like, that's the only possible case every single time. Yeah, root.left is on the left of root. The right is on the right, so this is false. Like this, I'm only affecting subtrees that are on the right. Left height. Like, that's wild to me. Bro, like how, like it's impossible for this to be wrong. I just don't get it. Like root that left. Literally, you delete that left subtree. So, the height of the root is, you know, whatever's on the right, even if it's none, add 1, add the current depth that it takes to get to that. That is the full height. Either it's, you know, you take that path, whether you're on the left or right, take case 2, which is the other biggest height the root can be from the other side of the subtree, and then this is crazy. Like, how is this possibly wrong? It's not, it's like impossible for it to be wrong. It's just, I'm also knowing the best shape to solve this, like, at all. At all. Like, my mind's not sharp right now. Maybe I sleep on this. But then again, oh gosh. Yeah, left, left, right. Right, right, left. Right, left, left, right. Like, I don't have a typo. Right, it's not like I'm messing this up. Like, it's a, like, of course I'm not messing this up. Of course I'm not. Just how is there a case where I'm failing? Like, that's insanity. Left, right, left. We go crazy. Otherwise, it's like, you know, this is all I can think of, you know, print Armageddon. Oh yeah, it's not now. Yeah, I hit a bunch of Armageddons. And the point is that, like, I'm updating the left and the right child, and I'm not updating myself. But that's exactly how I want it, because it's like I don't update the root, and I take care of the root's two children. I solve everything because from then on. It's just wild. It's like it's almost making me doubt whether I computed the heights correctly. I don't do his left anymore. Populate heights. I genuinely do not understand why my solution is incorrect. I just genuinely do not. Genuinely. I cannot understand why this is wrong. These are the only two possible heights. Six and four, huh? Oh. It's like the right of the root might be something like 4. Then on the left, I might delete something that happened to be actually insignificant. So the height of that subtree is not actually just the one that I deleted. I have to go up to the parents. Okay, I understand why it doesn't work. If, you know, one half of the subtree is supposed to be very short, with the original root, right, when case 2 doesn't win, and I happen to delete a part of the tree that is insignificant, then my solution will fail. Oh my goodness. But then it's the whole ordeal if I need to go to the parent until it fails. But then the problem is like, okay, it TLEs, right? Because it's essentially, if I do that, it's my first submission. TLEs, okay. So yeah, I have to abandon ship on that idea. Which means I have to get inspired by something in here. Okay, honestly, maybe I just leave this off to tomorrow. I am not in a mental shape for critical thinking at the moment. So like, please forgive me. It's just I cannot critical think. It is 2 in the morning. I'm exhausted. I cannot think straight right now. Maybe tomorrow I think about it. It's like, you know, super obvious, clicking the boom and so on. But it's just like I'm just wasting time for no reason at this point. If I haven't come up with it yet in this current state, I'm not going to come up with it anytime soon. So for you guys, it'll just be 1 second, but for me, I need to take a little break and at least just sleep over on this. So see you guys in literally just 1 second. Hey there, I'm back. Okay, let's get back straight into this problem. This is morning time now. I just woke up. Right, you're given the root of any tree with n nodes. Each node is assigned a unique value from 1 to n. You're also given an array of queries of size m. To form n independent queries, yeah, remove the subtree root at the node. Yep, yeah. Okay, I remember this problem. Okay. Oh yeah. Yesterday we came across, you know, that incorrect case. So here, if I run this, then yeah, 5 is incorrect. So this was incorrect because if you have something like, you know, 4, and this has like, you know, height is equal to 4, let's say, right? And this is like height equals 12. Right? Then it's like, you know, here it's like, you know, space. It's like h equals 10, h equals 2. It's like, yeah. Or 5, h equals 2. And then here it's like h equals 9. Right? Where it's like just where h means height, right? So it's like here it's like, okay. Like, yeah, I delete something in the left subtree. So worst case, you know, root might still be the height of whatever's on the right, right? But then if I come here and I'm like, okay, I'm going to delete this subtree, then it's like, okay, I'm like, oh, the new height here is actually equal to this height plus whatever was the, well, actually, the parent left height plus 1. I guess this is a bad example. It's still 8, and here there's like equals 20, h equals 21. Or maybe these, and this equals h equals 90. It's like the problem here is like, yeah, it says a height of 4, but over here there is, if I come here, I'm like, oh, I'm to delete this node here, right? Well, now I'm going to say, okay, well, this guy's new height is going to be whatever's on the right. So here, this tree has a height of 21, plus 1, so this has a height of 22, plus the depth it took to get here. In this case, there's 1, 2 edges. So this will be 22 plus 2, right? And so that way I'm like, okay, it's the max of either, since we're deleting something on the left, here we're deleting, you know, the h is equal, well, here we say, okay, on the right of root, there's a height of 4, right? And here on the left of 8, we're deleting this height equals 20 subtree. So 8's new, well, actually, let's pretend we're deleting, you know, something of height 30, right? Where it's like you actually affected 8, right? It's like, oh my goodness, we're deleting this. Actually, let's say that this is, you know, 40, and this was actually 90, right? We're deleting a huge subtree here, right? And here we're saying, oh my goodness, we're deleting this 90, which is actually what the old, like, you know, root height was. It was 90 plus 1 plus 1 plus 1. Sorry. And then it's like, okay, since we're deleting this subtree of height 90, we say like, okay, 8's new height is going to be whatever's on the right, even if that's none, because none has a height of -1. We're going to take that height, here in this case it's 21, add 1, so h's height is now 22, plus the depth it took to get to 8, which is 1, 2, so it gives an effective height of 24 on the left side of root, right? And so then we're like, okay, the max of whatever was the right height of root, 24, and then this new height. But we failed to account for the fact that, hey, there was another height here of size 40 that actually is root's new max, right? And so you'll notice that here, all we have are underestimates. And that's because that's what's going on, right? So that's the edge case we're failing. So at least we know the edge case we're failing. But the hard part is, how do we fix that edge case, right? Oh gosh. So, and this doesn't necessarily have to be here, right? This could be nested even harder. Although if it's nested even harder, this will still have a height of 40. So maybe it's like, well, okay, right? I guess we could do something like this, where it's like here we're deleting like a height of 90. So maybe these are like, you know, okay, these are levels. We're deleting a height of 90 here. It's like we can't just assume that the new height is going to be dependent on what was on the right of the node that is parent to this one, right? Essentially, it's going to be whatever was, or whatever is, the biggest remaining height, right? And if there is no remaining height at that level, then it's just none. Huh. So maybe we use like a max heap. Trying to think. Although, okay, that's an idea that seems kind of promising. So yeah, like here we're naively saying, oh, this will be the basis of our answer from then on, and then whatever was on the right of the original root subtree. We're failing to account cases like these. Oh shoot! I also really have to use restroom. Yeah, I do kind of like that idea. So yeah, because I was gonna say like, okay, what if this h, you know, is more nested down below? But that's not really the case, right? If the child here is, you know, like h is equal to 39, like, you know, this is whatever value you want it, right? X, 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 I don't know what it is. The point is, this is height 39, this is height 40 anyways. So this height actually kind of matters a lot. And why does it matter? Because this is the level, right, or the depth at which we're deleting something in the tree. That's actually... And if this has a height of 4, that means there's going to be, you know, nodes here at this level you know, that's like, you know, something that will be at a height of 3 here, and something will be at height of 2 here, whether it's left or right subtrees. But yeah, we can have things at a level here. That's interesting. Or so maybe we could grab like a max heap based on height of the nodes. Oh, wait, that could, okay. Maybe sleeping in on the problem does help. Even though I'm a little tired, fresh new eyes is fresh new eyes, no matter what. Okay, that's good. Okay. I'm trying to think now. So we have all the heights of the nodes. So now we need, okay, we need maximum heights per level. And then what if I delete the max height? Okay, so maybe per level, each level I map to a max heap. Okay, we can do something like that. Yeah. Okay. We'll call a method called self.populate levels, which we do after heights of root. Here we'll have self.levels. These are like, you know, column levels, column depths, column even like, you know, opposite heights. Like the depth of a node is like, you know, it's like the inverse of height, right? Where it's like 1 has the highest height but the lowest depth. 3 has the second highest height but the second lowest depth, right? So it starts at depth of 0, depth of 1, depth of 2, etc. Or level 0, level 1, level 2, etc. I call them depths, levels, it doesn't really matter. Populate levels, self, we take in a root, if not root, return. Actually, we're going to take in a depth is equal to 0. Okay, maybe we call this depths later on. Self.levels, depths, self.populate levels. We'll call it populate depths. Okay, there we go. If not root, return. It'll say if depth not in self.depths, depths dot self dot depth of depth is equal to an empty array, right? Here we'll do heap q dot heap push into self dot depth of depth. And since this is a max heap, we're going to simulate it using negative numbers, right? We just always have to remember that. That's a little trick I talk about in my channel. If you want to simulate like a max heap, you know, you take a min heap, which is what's offered in Python, you multiply all the values by -1, right? So what used to be the smallest, which was the 1 here between 1, 2, and 3, now -3 is the smallest. So that's what you pop using a min heap, and then you multiply this by -1, and there you go. You were able to simulate a max heap using a min heap. Sorry. Okay. Heap push, so now we want what? Like tuples of, we want nodes and their heights, right? Or just, yeah, okay, so yeah, root height is equal to self.height of root. So here we'll put negative height, and we'll put that root node, or at least root node value, right? Because we can always look up a value to node and of one time using our num to node dictionary here. Okay. Otherwise here we'll do self.populate depths of root.left with depth plus 1. Self.populate depths with root.right with depth plus 1. Return, right? Okay. Okay. This is a long function. Long function. Okay. Print self.depths. Return empty array. Okay. But yeah, 1 is at a depth of 0. At a depth of 1, we have 4 and 3. Yeah, that's good. Yeah, and 4 is a height of 2, which is good. 3 is a height of 1. Yeah, we have 5, 6, and 2 at this level. And we have 7. So we essentially have each node at each depth, and the one with the biggest height in each level. Okay, this is good. We have populated the depths. Now let's think. We gotta think back to this example. So if I delete something like 90, I want... Okay, if I'm left, that's... Oh, no. This is good. Actually, this is perfect, right? Because these are the depths, right? The height of the root node. So like, let's take something like 7, right? So the height of this guy is what? One, 2, 3, right? So yeah, 3 plus a height of 0. Or does this not work? What is... Oh, 6 is a height of 0. But 6 plus 2 gives you the full height, right? 5 has a height of -1 or 1. 1, 2, 3. Yeah, that doesn't really work. Why does 5 have a height of -1? That's not correct, right? Or, wait, what? Height. Oh, it is a height of 1. It has 1. Oh my goodness. Okay, I'm tweaking. Okay. Then yeah. One plus 2, yeah. And 1 plus 1, so there was a height of 2. But yeah, some idea like, you know, depth plus that height, like we were doing before. Okay, it's not gonna work as simply as I thought. If I delete 5, for example, 5 had a height of 1. So now I need the maximum at its level, which is what, 0, 6 or 2, doesn't matter. Take that height. Man, I also really have to use restroom. Okay, take that height. You take that height because, okay, we're no longer allowed to use 5. So then, yeah, the height becomes, you know, you take max in here, you add a depth of 2. That does hold, right? If you delete 7, then there's nothing left in the heap. So then maybe, what do? Do you go one level above? Or no? You just deleted the last thing at that level. So the maximum depth becomes 2, so the new maximum height becomes 2. Okay, that's cool. So if we delete the last element, then that's no biggie. That's no biggie at all. It's not a biggie in the world. I'm just trying to like, you know, go over these cases in my head. Maybe I look at case 2 as well. Give me some better information. So 0, or no, 5 has a height of 3. 1, 2, 3, yeah. It's like if I delete, yeah, okay. I gotta be careful, right? So if I delete something like this, I need to get the maximum depth at my level. Or maximum height at my level. Just why in like case 1 for 5, this is the one that was bizarre. Actually, no, that is work. It has a height of 1 and I add a depth of 2, which is exactly the root's height. But then if I get rid of, yeah, no, this does work. This does work. This does work. Yeah, if I get rid of this height, it's like I take the maximum of my level, in this case it's 40. After I deleted this one, whether or not it was actually my max. Ooh, so then maybe I don't use a max heap. Or no, I use a max heap and then I look at like, okay, is the maximum element myself? If so, I delete. And then get the new min, right? And then push it back because you don't want to lose data. Otherwise, if I'm not the max, then cool, the max stays. And so the height remains unchanged. Okay. I think we can implement an idea like this. Okay. This is not too bad. Check. Populate depths. Fruit left, fruit right, south and ends. Yeah. So this is tree queries. What do you call this? Like self pre-compute? Or no. We do something like this. Okay. Answer is equal to this. Return answer. For val queries, we're gonna say, hey, node is equal to self dot num2 node of val. Right? I need a node's depth, right? Here we'll do depth, but we'll also say depth.num2 depth equal to this. Okay, actually fine. Num to depth is equal to this of root of val is equal to depth. There we go. Depth is equal to self.num to depth of val. There we go. Maybe we don't even need this. So now we're at the correct depth, right? So now here we'll say if length of max heap is equal to self.depth at depth. If length of max heap is equal to 1, first of all assert that max heap at index 0 is equal to what? Here we'll say height is equal to self dot height of node. Negative height and the node dot val itself, right? Then here we'll say answer dot append depth -1, right? So it's like in a case where it's like if we like in case 1, if we delete 7, and it's it's the only guy at its depth of 3, right? Then that means no matter what, the maximum depth in the rest of the thing is 2. Oh no, but it has to be 2, right? Because if 7 was the depth of 3, its parent directly must be of level 2. So there is at least one thing at level 2. Okay, so we don't have to worry about that edge case. And so yeah, and that becomes the newest, deepest node. Therefore, that's the root's height. Okay, cool. Okay, cool. And then here we'll do continue. Whoops. Otherwise, this is not max elements. Height is unchanged. Or if it is max element, from heap, get newest max depth, get newest max height at depth. It has to work. Again, like I'm trying to think of like what if there's something deeper. The point is that these trees, anything smaller than that will have smaller heights because they contribute to that depth level's height. I keep trying to like counterexample myself, but I don't think there is one. Height is unchanged, or if it is, oh, okay. I mean, don't say things too quickly, right? Because that's what I thought yesterday, and I took a big bullet in the mouth. But let's keep going. Or if it is max element, pop from heap, get newest max height at depth. Right. And there's at least one more thing at this depth. Right, and it doesn't matter that this is not the deepest depth. The point is that, like, even if it's not the deepest depth, right, even if it's 1, the point is that these heights reflect the fact that, like, these heights are built off of the information that are these deeper depths, right? So it really matters what you get rid of here, because that's like what'll be the highest height remaining in there. Get newest max height at depth. Pop from heap. And answer goes back to heap. Continue. Okay. This is not max element, right? Of 0 doesn't equal, negative height comma val. First of all, assert that negative height comma val in max heap to do remove since of n. Right, for now it's just I'm debugging, right? So I don't care about slow asserts. Now we'll do then this is unchanged. Actually, we can do height, max val, heap of 0. No. Let's relax. Actually, we could do something like that, right? Where it's like this. 0 doesn't equal that. Then it's like so yeah. So that append self.height of self.root val. Right? Or actually here I have the root of root. Otherwise, this is not the case, so it will say item is equal to heap q dot heap pop from the max heap. Remember to add item back. So here we'll do heap q dot heap push max heap comma item. Here we'll say, okay, h comma v is equal to max heap at index 0 equals negative h. Right. Answer dot append h plus depth, right? So if we delete 5, then yeah, the newest height is now, 0, yeah, which is great because this deletes, the 7 in there. So the newest height would be like, 1, 2, and then, yeah, that's perfect. And so that append 8, okay? So what happens if we run something like this? Okay, it works. Does it work for everything? Is it too slow still? Bro. It passes. Okay. She's asleep, so she can't even tell. Oh, that feels good. Okay. Although we're extremely slow. Okay. Okay, but now we have a solution that works. Oh my goodness. Okay, that feels good. I'm not gonna lie, that feels very, very good. Even though it's slow, that feels good. Okay, also, one thing I'm realizing that is complete overkill. With this max heap, oh, okay, well, first of all, these asserts are O of n, right? So if we get rid of that, that first of all should make our stuff way faster, because that is an insanely expensive assert. I'm actually surprised I didn't TLE with that. Okay, well, we went from 5k to 600. Okay. Now we're into the 38.21% beats range. Yeah. This assert was just a sanity check, but yeah, it'll kill all my gains. Okay, now we're roughly inside, like, this standard deviation of, this standard deviation of thing. Okay, beats 50%. This is good. We're back in normal territory. One assert screwed everything. Okay, yeah, drawing it out really helped out, right? That really helped. Where it's like understanding the edge case that I was facing. By understanding the edge case that I was facing, I was able to come up with an even cleaner solution. Okay, but there's a lot of ways to do this a lot better. So if anything, you know what? Why don't we restart the problem? There's a lot of good code in here, right? There is a lot of good code. Okay, we need populate depths. We don't need populate answers. We don't need isLeaf. We don't need populate left nodes. We don't need isLeft. Right, we need tree queries, of course. We don't need delete node. We probably need get node from val. We definitely don't need mark deleted. We definitely don't need is deleted. I don't know. Yeah, this is not used anymore. That is definitely used. Sure. Let's see. What do I actually use instead of tree queries, right? Okay, these can go away. It has to have a working solution, right? Yeah, this is gone. Okay. Answer is equal to this. Return answer. Then, yeah, I have... Okay. This point, yeah, that was a good comment, so let's keep it. Yeah, let's delete everything that's in here. Jeez. All these beautiful attempts at solving the problem that just did not work. Okay. So yeah, there you go. Okay. Here we can do h comma v is equal to max heap of 0. If h comma v doesn't equal negative height comma val, item equals heap q dot heap pop max heap, h comma v is equal to max heap of 0. Our heap push, we'll call this temp is equal to this, max heap comma temp. That way, I'll just do this. This still works, right? Gosh. What did I do wrong here? Oh. Negative h plus depth. What? Oh, now I need this negative height. Whoops. What? What's going on? Equals negative h. What? Equals negative h. Okay, I don't know why. Oh. Yeah. Okay. I'm done. I need to add the root's height. Yeah, let's just not try to be cheeky or clever or whatever. Then yeah. Just run. We have code that works. We submit. Okay. We gotta be careful. We can't get too greedy here. Okay, 620. There we go. First of all the asserts are gonna become hashtag asserts, just in case. So we don't need asserts anymore. How many times do I call this guy? Just once, right? So this can go bye-bye. If get parent, yeah, I don't need that guy anymore. Populate heights, I do. Populate parents. Okay, if I uncomment parent, I only need node once, and it's for the heights. So what if populate heights the root of val, the val will do self dot height okay. We will do a def get height self comma node. If not node, return -1. Otherwise, we'll do return self.height of node.val. Right, there we go. Now we have a get height function. So now let's just do self.height. That's our get height. Self.get height of node. Get height of the root node. Roots. Yeah, this is populate heights. Populate, populate, populate. There you go. And then inside of get height, let's say okay. Now let's run this. Non-type has no attribute val. Not root. You're -1. Get height of root. Okay, now do we need val? Root.val. Root.val. Does that work? Nice. Okay. Okay, so that works. There you go. Wow, okay, so we're really chunking down our running time complexity. Okay, almost 90%. This is good, and there's still more optimizations we can make. Now we'll just do get height is equal to root.val, root.val. Okay. populate heights can now become called get height. Okay. Submit this. We're just gonna keep making our stuff faster and faster and faster and faster. So we need that. We don't need num to node. We don't need left nodes. We don't need deleted. We don't need temp heights. We don't need answer. We don't need this. We don't need this. We do need depth, and we do need num to depth. Okay. Okay. Nice. We can also populate depths and heights in one pass, right? Do we need parents? Don't need parents, right? If I get rid of this. Yeah, okay, we don't need that guy. We're gonna keep making this faster and faster. Okay. So now we just have heights and, yeah. We're gonna do def, populate, heights, and depths. Self, comma root. We can also. Okay, wait, no. Well, for populate depths, we can do it iteratively, right? Using BFS. Populate depths, yeah. Populate heights, on the other hand, requires. Okay, I can also do populate heights iteratively with a post-order search, right? That way, I'll always have the two children that I need. Okay, we can work on that. Def populate depths iteratively. Comma roots. Is equal to collections.deck. Actually, we can also do DFS instead of BFS. That way we don't even need a collections.deck, right? So here we'll say stack is equal to this. It'll have root with a depth of 0, right? Node, comma, depth. While length of stack is greater than 0, node, comma, height equals stack.pop. Node.left, we'll say stack.append node.left with a, this is a depth with depth plus 1. If node.right, we'll do stack.append node.right with depth plus 1. Okay, so now we need these things, right? Node.val is equal to depth, good. And now we need, okay, yeah. Yeah, there we go. Ooh. You know what we could do? Oh no, it's the other way around, but we could use like a min heap, like, you know, only ever keep the largest 2. Right, while the length is greater than 2, keep popping. Because we only ever need the 2 maximum heights at a time. Okay. Okay, let's put this in its own space here. here we'll do negative height, no.val, heap push, yeah. Yeah, so we need the heights first. Yeah, so maybe we don't do them, you know, together, but that's fine. 2 parses. Musical depth. Yeah, just an array with that, otherwise we push this into it with no.val. Loop invariant. Update depths metadata. There we go. Now, so this works, obviously. But what about iteratively? Does that work? Does not. What are we messing up here? Oops, this should be, why does it even have a root? Wait, no. Well, first of all, it should be no.val. Okay, so that does work. Okay, I don't know if it makes our stuff faster, but now it's at least iterative, right? Yeah, okay, so populate depths is now an iterative algorithm, so that's cool. Call this recursively. Yeah, okay. Okay. So that's good. That's good. Now get height. Yeah, this should really be called populate heights. We'll get rid of this comment as we need. Okay. Now def populate heights iteratively. Self, root. If not root, return. Now we're gonna do important to do post order traversal. That way always have access to left and right children's heights first. Okay, there we go. So here we'll do self.populate heights iteratively of root.left, self.populate heights iteratively of root.right, and now we have access to left and right children's heights. Self dot right left is equal to -1 if not root.left, else self.height of root.val. And same thing with right height. right height equals -1 if not root dot right, else root dot right's value, root dot left's value. Height is equal to max of left height, or right height, plus 1. And then we'll do self.height of root.val is equal to height. Right, nothing special here. Variables are cheap. Okay, so this still works obviously, but now let's come up here. And now self.populate heights iteratively with root. Does that still work? It does. Now let's submit. Okay, it's not too much of a difference. I thought it would be, just because it's like, you know, iterative solutions usually almost always prefer to recursive ones. Okay. But yeah, it's important that we do a post-storage reversal, right? Like if we did something like this does not work. Like yeah, this does not work. Whoops. Okay. Right, like it's very important, right? There is no self.height of root.val. So yeah, a post-order search is very important here. So now we have populate heights iteratively. So we can get rid of this guy. We can get rid of populate depths. Then, of course, this will just become what we'll do heights iteratively, and then populate there we go. And we'll grab this stuff, we'll put it right under this guy. Okay. Just keep making optimizations. Okay. Now we don't need a lot of this stuff. We can get rid of this original idea. Maybe I keep it for my solution explanation. Value to height. Value to depth. As well as depth to max heap height, val each node at depth. There we go. Now we can get rid of this. Access to of 1 lookups. Okay, can get rid of this. Depth, height, max heap. There we go. Yep. Yeah. Yep, that gets. Yeah, answer is unchanged. -1 is now maximum depth, but hence also new height of root. Now it's like we're deleting node with maximal height at this depth. So get second highest height at this depth, since new root height will simply be this second highest height plus its depth away from root node. This is equal to temp. So temp -h, since using simulating max via min heap. Depth -h. Yeah, we don't need this value, doesn't matter. Here we'll say height comma val 0 comma 1. Of val doesn't equal val of height. H plus depth. Negative. So simulating max heap via min heap. Yep. Oh, we don't even use this. Okay. There we go. So now we can call this height righteously. Okay. Again, I'm trying to clean up my solution as much as I can. Okay, 477, 82.82%. Okay, so we're doing as many optimizations as we can, right? We may populate heights iterative. We may populate depths iterative. We use the heights to populate the depth levels, right? And also we use the, yeah. Now here's the thing. We only care about the two biggest stuff in there, right? Maybe, would it be more efficient if instead of a max heap, we essentially only keep track of, you know, the two biggest? And it's like, they both start off as like, you know, none or some random value. As soon as you find one element, then you know like, okay, that's the maximum height. As soon as you find a second one, it's the second max, right? So here we can have like, you know, def update max height at depth. We'll take a depth, take a new height. Max height, comma second max height is equal to okay, I know how to do this. I just also really need to use the restroom. Gosh, okay. Node. Okay. Right, okay, so we don't want to use a max heap anymore. We have num to depth. When do we ever use num to depth? 1, 2. Yeah, okay. We do need a depth for each query. Okay, cool. So that's needed. That's needed. But now this, yeah, we only ever care about, you know, we only ever care about like, oh, the max height. Oh, if it's not the max height, then, you know, GG. Okay, for each, we still need, you know, max height and its value pair, as well as second max height and its value pair, right? And at the beginning, it's like, you know, we have none nodes, right, as the max heights. Okay, I will literally just be right back otherwise, because I really need your restroom. So for you guys, it'll be 1 second. So yeah, just see you in just 1 second. Okay, I'm back. Let's get back into this. Oh yeah, we were gonna change this to be yeah, okay, we only need the 2 max heights, right? Because, or max, yeah, max heights, because it's only gonna be like, you know, 1 of 3 cases up here, right? It's like, if there's only one thing, you know, okay, maybe I have a helper method that's just like, you know, it checks all these things and so on, blah, blah, blah. Okay, yeah, I'll need to edit some code in there, basically. So, okay. If depth not in self.depths, I will say self.depths, depth is equal to, we just need 2 things, right? We need the height and node value pairs for the biggest and second biggest. So, you know, we could have like, you know, a dictionary with like biggest and second biggest, you know, we can have like, you know, a tuple, right? Even a list. You can also do this via min heap, right? And it's just like you keep popping the minimum stuff, so that the last 2 things in the min heap are always the smallest, right? You can also do that. You know, let's think about this. Yeah. And here we'll just have height. Else if length of greater than 2. Here we'll just have a while loop for now, just in case. Heap q dot heap pop. And this guy. Right? Or we just do something more clever here. We'll just do this. Min heap is equal to self.depth of depth. Min heap will push in the height with its value. Heap q dot heap pops from the min heap. Right, so now at a depth we always have the max 2 heights, right? Because we keep popping from the heap as long as, you know, there's more than 2 elements. This I will be able to change to an if, right? To do change to if statement, right? Because the point is like each iteration, and it's like, you know, log n time, but it's log base 3 constant time. Okay, so yeah, just constant time a lot of times, but technically since the height is at most 3, then there you go. So now we can do something like this, right? Like the max heap is equal to 1, then yeah, this remains. Does it equal to val? Assert length of min heap is equal to 2. But this is now actually min heap. This is a min heap. If min heap of val doesn't equal val, answer is unchanged. Otherwise, we don't need to do this. We don't need to do this. We'll do min heap of 1's height. 1, since only 2 elements. 0 is smallest. Wait. We gotta be careful because 0 is actually the smallest, right? So 1. And here is 0, right? So this is the smaller height. I gotta be careful. Okay, first of all, let's try running something like this. Okay, first of all, we don't need this guy. This is self.depths. Depth. What? That's wild. Oh. Can I not do that? Like, does this not work? Oh. Oh, wait, I'm dumb. Of course this is not the case. Yeah, this is min heap. Of course this is not the case. Equal 2. It should be print length of min heap. This might be less than 2. Just might confirm my suspicions here. But yeah, 1. Yes. It should be less than or equal to 2. And yes, this is accepted. Okay, beautiful. Now let's submit this guy. And wow, okay, 90.77%. That actually helped a lot. Hey, happy girlfriend, okay. since min heap is at most 2 in length, equals 1, or length of min heap equals 2, i.e. 1 less or equal length of min heap less or equal to 2, right? In this case, min heap is of length 2. Since this is a min heap, the node with smaller height be at index 0, and the one with bigger or equal at index 1. Hence, here we can do max height val is equal to min heap at index 1. Now we do second max height val is equal to min heap at index 0. So now if max height val otherwise, we get the second max height. Since val is the with max height at current depth, need to update oh, careful. Of course. Here we go. Since val is the value with max height at current depth, we need to update need to update max height at current depth. Yeah, we're deleting the node with maximal height at this depth. It means that the second highest height is there. Root node. Second max height there we go. There we go, and there we go. And there we go. Okay. Now submit that guy. And okay, perfect. right? Otherwise, it's like, you know, this is essentially an else. Else. So it's max height at depth remains intact. There we go. We can get rid of this assert. Yeah. We can get rid of that. Yep. Okay. Pre-compute needed heights and depths metadata for each node as well as first and second biggest heights at each depth needed for queries. Okay, I think our code is looking very beautiful now. There we go. We've got some comments. And excellent. So now we've got our populate heights helper. Yes, we've got our populate heights helper. Our populate depths helper. Yeah, this is no longer needed. This is all one block. This can change to an if statement. Yeah. Loop invariant. Yeah, this test case I'll need for my explanation. Yeah, there we go. Submit this one more time. Okay, there we go. 92%. Very nice. Very cool. Okay, so we have a very, 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 very efficient solution, which is amazing. Okay, let's try to think if there's anything else I want to change, but likely not. And so this becomes a 90 line of code solution. Okay, so forgive me for my sickness, but okay. As always, in all my videos, I do a quick recap of how I was able to solve the problem. This was definitely a little bit of a challenging one. So for context, I started this problem with an hour time limit because me and my girlfriend were going to a Forest Black concert. That was very awesome, by the way. And I actually was solving a wrong version of the problem. I did not realize this specific note over here, which says that the queries are independent, so the tree returns its initial state after each query. I thought that, you know, after performing the ith query meant that, like, you know, when you perform the ith query, you've already performed query 1, 2, 3, all the way up to I beforehand, not including I, and then you're doing query I, right? So it's like you keep deleting chunks of the tree over and over and over until the tree gets, you know, very small. And but that was completely incorrect, where it's like the queries are actually independent of one another. Once you've you know, taken a query, it's like it does not actually affect the tree, right? You just return what the new height of the root would have been if you executed that query, but you never actually execute the queries themselves where you delete stuff, right? They're queries, they're not like update operations. So that was a complete misunderstanding from my part. So yeah, you need to do this problem where you realize that the queries are independent of another, right? And then the height of a node is essentially the number of edges in the longest path from it to a leaf, or from that node to the root, right? So for the root itself, since it's already there, it's just 0. No, sorry. Yeah, forgive me. But the height is essentially the path from the root to the longest leaf in terms of the number of edges in between there, right? So here it would be 1 edge, 2 edges, 3 edges. So there we go. That's the height. Okay, and which is also known as, you know, the deepest depth, right? Where it's like if this is a depth of 0, these have a depth of 1, these have a depth of 2, this has a depth of 3. The node with the deepest depth essentially represents the height of the root node, right? So that was a clever little thing that I utilized later on. Okay, let's get into the solution explanation. So yeah, the very first hour and a half, I was solving a wrong version of the problem, so that was my bad. And then I had a realization where I told myself, like, okay, what if we realize that, like, hey, when we delete a part of the tree, we need to update that fact and essentially give it to the parent node, right? So one thing that I tried is essentially it's like, hey, whenever I'm gonna, you know, for each node, I grab its, you know, I compute, you know, its height, I compute like a lot of metadata, one of which is essentially a node's parent. So for each node, I create a hash map where I map the nodes to their parents, and I thought my solution is like, okay, we're just gonna, whenever we delete a node, we'll go to that node and we'll essentially say, okay, let's update its parent's height. We'll update that parent's height. We'll update that parent height, right? And keep going until we get to the root node, right? And that way we'll have updated the height of the root node. And that way it's like for each query we get the right answer. The problem with that is that it's too slow, right? The point is that, like, for each node you have to traverse upwards through the tree, right? In the average case it is log n time. So it's like for each query you do log n work on average. So it's like m times log n, which should work and so on. But in the worst case, right, they could keep asking you the query with, like, you know, maybe you have a chain like this, 1, 3, 2, all the way down up to all n nodes, and maybe they keep asking you to query the last one, right, or the last one, second to last, and so on, and in which case it's like you have to keep traversing up the tree every single time, which happens to be all n nodes, all for all m queries. And then it's like n times m running time complexity, even though on average, you know, traversing the parents all the way up to the root node should take log n time on average, it can be worst case O of n. So my solution isn't m log n, it's mn, which happened to be too slow. So that solution, albeit correct, was time limit exceeding, right? And so then I thought, okay, what if we take an example like this? And it's like, okay, if I know, like, here I'm deleting this subtree with a height of 90, right? So h equals something just means, like, you know, the tree here has a height of 4, the tree here has a height of 90, which is the left of 8, right? And then it's like, okay, if here I delete this height, then I'm like, okay, this actually used to be, you know, the biggest height. And then I was trying to think, if I delete this node, then okay, maybe the height is like, since we're deleting a subtree that is to the left of the original root, let's keep track of what was to the right of the original root, which was a height of 4. So the height of root is at minimum, you know, height of 5, right? Because it's just this height of the subtree plus 1, and since we know we're deleting something in the left side of the root, we know that this won't be unaffected, so we know that the minimum height of this is a 5, right? Then when we delete this, I'm like, okay, let's go to the parent. We'll set the parent's node value to essentially be equal to, okay, if we're deleting the left side of this parent, then we're going to take whatever's on the right. Here on the right, it happens to be, you know, a subtree with height of 21. By the way, I say none is a height of -1. That way it's like -1 plus 1 is equal to 0. That way it's like if something is a leaf node, it becomes, like if I have something like this, right, and it's a leaf node, and then I take, you know, the height of the left one is, well, the height of none is -1, -1. I take the max of those two heights, which is -1, and then plus 1 is equal to 0. That way I can essentially assign a leaf a height of 0. So if a node is not there, I give it a value of -1. Otherwise, if it's a leaf, it's a height of 0, and so on. Blah, blah, blah. So here is just a subtree that happens to have a height of 21. So it's like, okay, since we're deleting this subtree, the new height of this node here will essentially be this right subtree plus 1, right? Which is 21 plus 1, which is 22. Then I'm like, okay, for each node, I also have access to its depth, right? I'll explain how I do all these things, but for now, just bear with me. I also have access to its depth, which essentially represents, you know, how far away it is from the root node. Well, if this guy's new height is 21 plus 1, which is 22, I can also add to it, you know, how far away is it from the root node, i.e. its depth. In this case, it's 2, right? So 1, 2 away. Then I know that, like, there's an effective height of 24 up in here. And 24 is bigger than 4, and therefore I would return 24, right? Now, here's the problem. There was a subtree here with height 40. Since this is height 40, that means this actually has a height 41, 42, 43. The biggest height of the root node is not 24, it is 43. And this made me go nuts yesterday, right? I was wasting my entire time. I was like, why is this not working? Like, it's either, you know, since it's in the left subtree, I'm not editing the right subtree, so it's either, you know, the height of this guy plus 1, or it's like, you know, I have this guy, I calculated its height perfectly, I have its depth and so on, I have its right subtree because I just deleted its left one, I know its new height and so on, so the new height of the root, what is going on? Well, I failed to recognize the fact that, like, you know, some other part of the tree, like, might have, like, here that I didn't consider, right? I considered this part, but I didn't consider stuff that were in here, right? And so this has a height of 40s, and so this one is the one that's actually going to contribute to the final height of the root node, right? So then that's when the aha moment went inside of my brain, and I'm like, okay, when I delete something, I need to know at what depth I'm deleting that thing, right? Because currently it's like, whatever the stuff is at this depth, right? So this is depth of 0, this is depth of 1, this is depth of 2, this is depth of 3, right? So these are 3 away from the root node, right? So this is of height 90, it's 3 away from the root node, so 90 plus 3 is equal to 93. That's essentially the height of the root node at the moment, right? Because it's like, you can take 1 edge, 2 edges, 3 edges, and then here there's at least one path with 90 edges below, right? So the height of the root is equal to 93 in this case, right? So then it's like, okay, every single node that is at this depth, I need to consider, if I delete this guy, what is now the maximum height that remains at this depth, right? Because with that information, I'm able to essentially query, like, hey, what is the new height of the root node, right? Because it's like, if I delete this 90 and I make it go kapoof, then it's like, okay, I can, at this current depth, right? Anything with a higher depth, I don't care about, right? Because again, they're at a higher depth and so on. I want to go to this depth where I'm deleting the root of the subtree, and I'm like, okay, for every single one of the nodes that are at my same level or same depth and so on, it's like, what are their heights? Take the one with the biggest height, and then essentially depth of that node plus its height is going to be the new height of the root tree, with what the node with the highest height inside of this depth level, right? Here it happened to be 90, so the height of the root had to be 93. If I delete something like, you know, this h equals 40, the height of the root is still 93, right? Because this was, you know, the one that actually impacts the height. But if I delete this one, it's like, okay, which node at this depth is now the one that's going to contribute to the root's height, right? And so that was the thing that I realized. One thing, first of all, is if I get rid of these guys and I get rid of this guy, well, then it's like, okay, if I delete this guy completely, that was the only thing I had at this depth. Well, we know that the maximal depth that remains is whatever depth this was minus 1, right? And we know that, like, there must at least be one node at this depth, right? Because if we're deleting this subtree must have a parent, this 8, so there will always be at least one node at the depth that was right above the one that we deleted the subtree at, right? So here I have a check in my code that says, it's like, you know, okay, ignore the technicalities here, but, like, you know, if length of the min heap is equal to 1, I only had one thing at this depth that I'm just about to delete, then I know it's like, okay, depth minus 1 is now my new biggest depth inside of the tree, and the biggest, you know, as I said at the beginning, the depth of the biggest depth inside of the tree is also the height of the root, right? Here, 7 is a depth of 3, which contributes to that, you know, height of 3 of 1. Of the root node, right? So hopefully that makes sense. And so now, if I delete the last thing inside that depth level, then it's very easy, right? Depth minus 1 is now the biggest depth inside of the tree, which is therefore also the new height of the root node, right? But things get a little trickier, obviously, if it's not the last one, right? In this case, it's like, okay, let's suppose that we delete something like 40 here, right? Well, if we deleted that 40 in here, well, check this out. We still have our height of 90 here that contributed to the root node. So if we're not deleting the subtree with the maximal height at this depth, then there was no effect to the root node, essentially, right? So in this case, kaput, we're just done, right? We know that the height of the root of the tree is still 93 in this case, right? Because we did not delete the subtree at this depth with maximal height, right? So here in my code, I say, you know, if val is equal to max height val, I do some stuff. Otherwise, it's like, oh, my answer is not changed, right? Because it's like, my goodness, I still have that maximum height node height subtree inside of this depth level and so on, I did not delete the one with the biggest one. So it'll have no effect on the height of the root node. So therefore I can just continue, right? So in this case, it's like, do nothing, insert an append, the height of the root node that it currently is at, don't delete anything. There you go, bada bing, bada boom, life is happy, right? So that's essentially that. Oops. Now, where things get obviously interesting is, okay, what happens if at a certain depth I delete the tree with the largest height, right? So in this case, if I delete this guy, right, x, I've deleted the subtree here at this depth. Depth is equal, so this is, depth equals 0, depth equals 1, whoops, depth equals 2, depth equals 3, right? So this is depth 3. Right, and again, like there's more depths, right? Because this is of height 21, so there's like, at least one node at depth 4, at least one node at depth 5, so on, etc. It's just, I'm doing this for convenience sake to show an example, right? Then, essentially, I'm like, okay, I deleted the subtree with the biggest height here, right? So what is the height of the root node at this point? Well, okay, we covered the case already if we deleted the last thing inside of here, right? If there are no other heights, if there are no other nodes at this level, then we know that the highest height will just be the depth minus 1, right? We already covered that case. We already covered the case if we don't delete the highest. Now we have deleted the highest. So what happens? Well, since again, we've already covered the case where there is nothing left, so there's at least something left, right? So here in this case, there are 3 things that are left, right? This node with height 40, this node with height 21, and this node with height 2, right? So then ask yourself, what is the height of the tree now? Well, in this case, it's going to be whatever is the remaining maximal height, right? Because it's like here, it's like the height of the tree for each of these ones. It's like, okay, you know that to get to any single one of these nodes, it's going to take 3 edges, right? Because it's a depth equals 3. For example, h is equal to 21. It'll take 1 edge here. That's 1. 1 here, so that's 2. 1 edge here, so that's 3 edges, right? Same thing for here. 1 edge, 2 edges, 3 edges. 1 edge, 2 edges, 3 edges. I didn't do left and right subtrees here because I was lazy, but you get the point, right? So here's the thing. Since all of these take 3 to reach, the height of the root node will essentially just be the maximal one of these nodes in here, heights plus the depth that it took to get to that node from the root, right? It takes 3 to get to any one of these nodes, and then whatever their height is starting from there, well, that plus the depth it took to reach that node from the root node will be the height of the root node, right? So essentially the answer will just be, out of every single node here at this depth, take the one that has the largest height. In this case, it is h equals 40. And then we know it's like, okay, this has a height of 40, and we know its depth is equal to 3, which means it took 3 edges to get to this node from the root, right? Again, it's like 1 edge to the 5, 1 edge to the 1, 1 edge to the 4. So that's 3. So it'll be a height of 40 plus 1, 41, plus 1, 42, plus 1, 43. So the height of the root node will just be the height of the node with the maximal remaining height at this depth level plus the depth, because that represents the length of the path to get from the root to any node at this depth level, right? Hopefully that makes sense. And then again, the way that I check these things is like, okay, I used to have a max heap, right? And it just kept, like popping, pushing as I needed and so on. But I realized I only ever need the largest 2 heights at any single point in time, right? Because here it's like, if this is h is equal to 90, well, it's like, okay, if I just keep track of the largest 2 heights, then that's all I need, right? Because it's like either if I don't delete 90, then the answer is unchanged, right? So there we go. And if I do delete 90, then I only need to know the maximal height from that point on, right? Which in this case is equal to 40, right? So it's like, it's very nice in that way, where it's like, if I don't delete 90, the answer is like the one with 90. If I do delete 90, then it's going to be the second largest one, which is 40. So at each depth, I only necessarily need to keep track of the largest 2 heights, right? And that's all that I need, right? And then once I have that, I'm able to solve the problem, right? Because it's like whenever I delete a node, it's like, okay, is it the last one inside of this depth? If so, then it's just depth minus 1. Is it the biggest one inside of this depth? If it's not the biggest one, then that means the height of the root will remain unchanged. If it is the biggest one, then let's grab whatever is the second biggest one, because that is now the one that will influence the root's height. add to that height the depth, because that's how many edges it takes to go from the root to any node inside of this depth, including the one with the second maximal height, and then just return that answer, right? So essentially here, ignore how the fact that I get heights and depths for now. Essentially here, it's like, okay, answer is going to be equal to an empty array. For each value in queries, right? These values represent node values, right? Essentially, it's going to, ignore how I do this for now, but essentially I get the depth, the height, or the heap representing a certain depth all in O of one time, right? And the heap essentially here, for context, is essentially of maximal length 2, which represents the first and second biggest, sorry. Essentially, this is a min heap, true, but this represents the first and second largest values, sorry, the first and second largest value pairs of height and nodes at a certain depth, right? So it's like for each depth, like this is at most length 2, this min heap, and essentially it just contains, you know, the two biggest height and node pairs. The reason I use a min heap is that way it's like, you know, I keep popping for the min heap as long as its length is greater than 2. That way the last remaining 2 elements will be the 2 biggest ones, right? Because again, that's all I need at every single depth. And so then I check like, okay, if the length of the min heap is equal to 1, that means there's only one element and I'm about to delete it, right? Since there's only one element and I'm about to delete it, right? It's like, it's like if I get rid of these guys, right, I get rid of 1, 2, 3, 4. If I delete this 90 here, right? Delete, it's gone. There's nothing left at this depth anymore. So this is the maximal depth. And we know there's at least one element because whatever node I deleted in here, it must have a parent, right? Which is at the depth preceding to where I deleted the subtree. So this depth minus 1 will be this depth here. Well, these are the nodes with now maximal depth in the entire tree. Therefore, the height of the root will be just this maximal depth, right? And so that's why in this case, in this case, if the length of the min heap is equal to 1, then I just append depth minus 1, because that is now the maximal depth inside of the tree. Therefore, it is the height of the root node, because again, it's the maximal depth, right? It's like whatever the depth of the maximal node, as I explained at the beginning, will just be the same as the height of the root tree, because that is the reason why the root has that height. Right, so like in this example, a height has a value, a height of 3. Why? Because the path of the longest number, the path with the most number of edges is here with 1, 2, 3 edges to 7, with 7 having a depth of what? This is depth 0, depth 1, depth 2, depth 3. So you'll see the maximal depth in the tree is also the height of the root node, right? So that's why this works. Then it's like, okay, here I just do a little commentary, right? Since I'm using a min heap, this means that, and there's 2 elements in here, right? Because there's either 1 or 2 elements, right? Because the fact that I'm deleting a node means that it must exist at that depth and so on. So there's at least one element in there. If it's the only one, then like, you know, depth minus 1 is the answer. Otherwise, I have exactly 2 elements, right? And then since I'm using a min heap, implementation details, but for now just realize that I'm using a min heap. There's 2 elements in there. These are height and node value pairs. And it's like, okay, the smaller one will be first in the min heap, right? So the smallest value in the min heap is always at index 0. Since there's only 2 elements, whatever's at index 1, even though usually I can't do this in the min heap, I know that it's the biggest one because it's the one that's not at 0. So at index 0, I essentially have the smaller height. At index 1, I have the biggest height, right? So here I just make this my life easy. Maximum height and the value with of the node value with maximum height is equal to min heap at index 1, because again, min heap at index 0 will have the smallest height. There's only 2 elements here, so second maximal height is the one at index 0. And I don't care about the value of the node here and so on. I only care about the effect that it does on the root height. So that's why I do an underscore instead of actually putting a name there, right? But otherwise, the maximum height will be the one at index 1. That's why I do that. Then I essentially do the rest as I was explaining, right? If the value that I'm deleting, of the node that I'm deleting, is equal to the one with the maximum height at this depth, well then, this is where, like, you know, the hard part comes in. Otherwise, if this is not the case, if I'm not deleting the node with maximal height, then the answer is very easy, right? The answer is unchanged, like I explained, and we just return the current height of the root, right? So if I don't delete 90, right? If I delete, like, you know, h is equal to 40 here, well, it doesn't matter. The height of the root tree will still be 90 plus 1 plus 2 plus 3, which is 93, right? With the depth is equal to 3. So the height of the root will remain unchanged, so I don't need to do anything. Obviously, if I delete, the biggest one, that's when I have to get the second maximal one, and then, use that for my answer. So that's exactly what I do here. I say, like, okay, if val is equal to max height val, essentially I'm deleting the node at this depth with the highest height. Then I need to grab the second highest height, which again I have thanks to this little min heap stuff. And then whatever that height is, well, okay, it also is far away from the root. How far away from the root? Well, whatever depth it's currently at, right? So its height plus the length of the path from itself to the root, which is its own depth. Well, this will be the complete height of the root, right? The longest path from the root to a leaf will essentially be like, the path from this subtree to, a leaf, which will be, the second max height. And then from that node, how many edges are there between that node and root to get to it? Well, it's whatever its depth is, right? So that's why we take this second max height plus the depth, right? To get from the root to this node, it takes depth edges. To get from this node to the deepest leaf, it takes second max height edges, right? So the sum of these two is essentially the path with the most number of edges from the root to a leaf, therefore the height of the root, right? So that hopefully that makes sense. And then at the end, once I've done this for every single query, I just return answer, right? So now all there's left to explain is essentially how I did the populate heights and populate depths. Sorry, my nose is like really itchy. I was like, I keep trying to like, make the itch go away. So I really apologize. Okay. And then, yeah, so the only thing that's left to show is like, okay, how did I populate the heights, the depths, and the num to depth, right? And so here I used to have it recursively, which was a lot easier to explain and so on, but I wanted to, kind of juice up my running time here to make it as fast as possible. So I made it iteratively and so on. I was just trying to make every single like micro optimization I could make to make my solution as efficient as possible, right? So here I have an iterative solution, and the important part is that, the height of a node is essentially, it's like, take its take the height of the left subtree, take the height of the right subtree, take the maximum one of these heights and add 1, right? That's the height of any node, right? And so the way you can do this recursively, right, is if not root with return, return -1, right? That way it's like, if you have a leaf node, that way it's like its two children will both be none, both of which will have a height of -1. And then you take the max of those, which is -1, add 1, makes it 0, and therefore you return 0. That way it's like, any leaf will have a value of 0. Otherwise you could just do, if root is a leaf, then like, return 0, and then it's like, otherwise blah, 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 blah. But if you want to do this iteratively like I did, you need to make sure that you do a post or a traversal, right? Because to get the height of any node, I need the height of the left and right nodes, right? Even if it's not, right? Which means that, okay, if I do this, I need to essentially build my way from the bottom of the tree and upwards, right? Because for the root node, I need to know the heights of the one to the left and the one to the right, right? Which means, and for this guy, I need to know its right as well as its left, right? So, sorry, I'm trying to show an example. But it's like here, if this is my root node, I need to know my right height, I need to know my left height, and using both of those, I take the maximum one of these two and add 1, right? Because if this one is the maximal one, it's going to be the height of this guy plus 1 to get to the root node, right? So, given the height of the two children, I take the maximal one, add 1. That's the height of a node, right? And so essentially, I need to always have access to the height of the left and the height of the right. So if I want to do this iteratively, I need to solve essentially the heights of every node at the bottom of the tree, i.e. all the leaves, and then I can solve, their parents, and then I can solve the parents' parents, and then I can solve the parents' 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 parents, and so on, etc., etc., right? So here I do a post-order traversal, right? Before I try to compute the height of a node, I first call this function. Oh. Wait, I'm silly. I'm not doing this iteratively, lol. Okay, I'm doing populate depths iteratively. I wonder if we could do this one iteratively. We could have like a visited set, and so it's fine. For now, we'll have it recursively. Yeah, so Yeah, okay, this is funny because it's before I had it recursively where it's like, I'd call like I'd make this return the height every single time and so on, and now I don't, and so that's why I needed to do post-order search. Okay, I won't bother making it iterative and so on, but essentially that's what the way it works. It's just a post-order traversal, so it's like, fill in the values for the bottom nodes first, and then, do the parents pairs, right? So here, once I've populated the answers for root.left, once I've populated the answers for root.right, then I'm done. So here I do, okay, I get the height of the left child. If the left child, right, root.left is none, so if not root.left, then I give the height of a none node, -1, right, as I explained earlier. Otherwise, if it is not none, then I get its height, right, which I know must be populated because we've called self.populates height on root.left before, and if it was not none, it had to have a value added to it, right? And then here again, right height, if it's none, then I just do -1, otherwise I get its actual height because again, I called this, which means its height must have been populated if it was populatable in the first place, right? Then I take the max of these two heights, add 1, and that's the height of my current node, right? So root.val in this case, and that's essentially how I populate all the heights. Then for populate depths, I do this iteratively. You can again do it recursively. Essentially the way you can do it is you start with the root node, you give it a depth of 0, right? If not root, return. So it's like, the way you could do this recursively, because I think that's the easier one to understand. Self, roots. And here, BFS probably makes more sense, but I just did DFS because it works the same in that way. I don't have to use collections.deck. But here you can do something like if not root, then here like return. Otherwise it's like, depth, which is initially 0. And then it's like, okay, self.depth of root.val is equal to depth, and then self.populates depths with root.left, and then you give that a depth of +1, right? And then this guy with root.right, and you give this a depth of +1. So something like this would work, right? Where it's like, okay, you initially start with a depth of 0, so the root node has at any point if you see a none, you just return. You don't need to populate anything, right? Otherwise this root is not none, so we give it a current value of depth, and then we know it's 2 children, right? From any node, the depth of the 2 children will be just 1 more of the depth of the parent, right? So we just keep doing +1 and so on. So this is an easy way to implement the populate depths if you wanted to do it. I essentially took this easy idea recursively and made it iterative, right? So essentially I start off with the root node with a initial depth of 0, and then okay, I say like, okay, well the length of the stack is greater than 0, this is just DFS. I get my current node in depth, right? Height is equal to self.height of node.val, because again, I've already populated the height, so now I have all of 1 lookup types of each node value's height, again from this function. And then it's like, okay, I know that this value now has a depth of this, right? Because I popped the depth from the height because these are node and depth pairs, right? Here I do some extra work, so here I do my min heap work where it's like, okay, if the depth is 9 self.depths, then it's just an empty array. Otherwise my min heap is like equal to this, even if it's an empty array that I just made now. And I push the current height and node value that I've seen at this very depth inside of there. And then if the length of the min heap is greater than 2, then I pop, right? That way it's like I only ever keep, the 2 largest heights inside of my min heap, like explained before, as I need and so on. So this is just me doing extra work. But the really interesting part is like, okay, once I pop something, like a node and its depth, right? So here's like node and a depth. Then I say, okay, if node.left, right, if it is not none, if the left child of the node is not none, then I'm going to append that to my stack, and it's going to have a depth of +1, right? Because again, for any node, its 2 children are just going to be 1 more in depth value than the depth of the parent, right? So node.left is going to be the node's depth +1. For node.right, same thing, if it is not none, it's just going to be that depth +1, and that's it, right? And that's essentially how I'm able to do the same algorithm iteratively for the populate depth function, right? Here I could try to think about how to do populate heights iteratively, but honestly, I think it's good as is. I've already spent a lot of time on this problem, and I think I've gotten the juice that I needed from this problem. And then this, by the way, was the holy grail for me to solve this problem, because it helped me realize my bug, where I was like, not considering a case like this h = 40 here, so that I could go like my aha moment and realize like, okay, I just need to get the tree with maximal height at the depth that I'm deleting a subtree at to essentially get the rest of my answer. And that concludes my explanation for this problem. A little bit of a big one, but whew. Okay, and rightfully so. It's a LeetCode hard. The LeetCode hards are always a big challenge. I'm just glad I was able to solve it, and not only solve it, but solve it efficiently. So honestly, King Kong, that feels very good. But otherwise, that's pretty much, hey, thank you. That's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.